Right, good morning everyone. Okay, so we will continue with our lecture for today for reaction engineering. So last Monday we have done tutorial chapter 3. Okay, there's another one more question number 7. So question number 7 will be like a homework for you. So I leave 2 questions in tutorial chapter 3. Question number 5, question number 5 and question number 4. Question number 4 and question number 7, the last question as a homework for you to try on your own to see whether to gauge your understanding of chapter 3. So if you are able to do chapter 3 by yourself, then it should mean that you are okay for chapter 3 lah. Okay, so today I will continue chapter 4. Before I forget, this is already week 5, right? So I plan to do the test on probably week 7. So you have another 2 more weeks. So I will use just our lecture time lah. Either I will use Monday or I will use today time to do the test. Okay, so it will be on week 7. I'm not sure yet, either Monday or Wednesday, either Monday or the time today during our class time. I will confirm to you by next week lah, which day the test will be. So this is week 5, so next week 6. So you have another week. The following week after next week will be our test week for test 1. Okay, so we go to chapter 4. So probably by now you realize that the chapters are getting harder. Okay, so we have already settled the chapter 3, and you can also see the connectivity between chapter 1, chapter 2 and chapter 3. So even when you attempt the question in chapter 3, you will have to use the knowledge in chapter 1, the knowledge in chapter 2, and as well knowledge in chapter 3. So when we go to chapter 4 today, the same thing is happening. You have to actually use the knowledge that you have learned in chapter 1, chapter 2, chapter 3 in order for you to do chapter 4. So means kalau you don't really get it chapter 1, 2, 3, that is actually very hard to do chapter 4, and it's even harder because chapter 4 we need to actually derive equation. Okay, so that's the challenge dalam chapter 4 lah, sebab we have to derive equation, and this equation is not really straightforward. So the understanding of the equation is really understand, but as I said, you are not required to actually memorize the equation. Okay, equation tu when I teach you to derive, you don't need to actually memorize the equation. However, understanding the derivation is also important because then you will understand how these equations are applicable to what situation. So kamu kena faham every questions tu ada situation, it has its own situation. So let's say it's this situation, what formula that you need to use, so on and so forth. So if you tak faham situation tu ataupun perbezaan the equation, then it becomes a problem lah nak apply the equation. Okay, right, so I talked a lot about equation, right? So what actually you're going to do in chapter 4? So what you're going to do in chapter 4, we are going to now design the reactor, or we're talking about finding, of course, kalau batch reactor, we're talking about finding reaction time. For CSTR, PFR, we will talk about finding the volume or vice versa. So maybe in the equation, katakan you're given the volume, you're asked to find, let's say, the concentration or the molar flow rate, so on and so forth, depending on the question lah. But the equation correlates reaction time, correlates the volume of the reactor. Okay, so I told you just now that it's actually combination of chapter 4 is a combination of chapter 1, chapter 2, chapter 3. Okay, so let me explain now how does it correlate in chapter 4. Okay, so first of all, in chapter 1, if you remember, chapter 2, you remember, I have already taught you to derive the equation, the design equation for the reactors. So kita ada 3 reactors kan. So we learn design equation for batch reactor, we learn design equation for PFR, we learn the design equation for CSTR. So tu dah terbagi kepada 3. Means kalau kamu guna batch, okay, design equation batch. Kalau guna PFR, design equation PFR. Kalau guna CSTR, design equation CSTR. Okay, tu dah first. Okay, then next in chapter 1, you have learned about the rate law. Chapter 3, you have learned about the rate law, right? You learn the rate law, either first order with respect to A ke, second order with respect to A ke, or it can be first order with respect to A, first order with respect to B. So kamu kena faham, dia first ada 3 reaktor yang berlainan. Dalam 3 reaktor berlainan ni pula ada minus RA. Kamu perasan design equation tu ada minus RA kan? So minus RA ni pula terbahagi juga daripada rate law yang berlainan depending on the reaction. So mungkin untuk reaction ni rate law dia minus RA equals to KCA. Maybe for this reaction minus RA dia KCA square. Or this reaction minus RA dia KCA CB. So kamu tengok dah terbahagi lagi. Okay, then you don't forget the 3 rate law that I teach you so far adalah irreversible, means tindak balas yang tak berbalik. Okay, so it's also possible you will have reversible reaction. Means kalau reversible reaction, the reaction goes forward, goes backward. So kalau reversible reaction, it has its own rate law. Yang kat belakang ni kalau kamu perasan, the minus RA in bracket CA minus CB CC per KC. This is actually the rate law for reversible reaction, which kamu belum belajar lagi. Reversible nanti saya akan belajar at the end of this chapter. You will learn about reversible. So kalau reversible, rate law dia pun dah berlainan. So kamu faham? Katakan you have batch, right? So you have batch, you have depends on the reaction pula rate law yang mana. Kalau kamu ada PFR, kamu kena tengok pula rate law yang mana. So you imagine kalau rate law yang berlainan, the equation pun dah jadi berlainan. Okay, dah 3 reaktor dah berlainan equation. Setiap reaktor pula kalau rate law yang berlainan, equation pun dah jadi berlainan. Okay, so that's already make it a bit more complex. So kamu kena belajar, you have to learn to derive for each situation. Kalau batch KCA macam mana? Batch KCA square, batch KCA CB. PFR, KCA, KCA square, KCA CB, CSTR, KCA, KCA square, KCA CB. So that's already 2 scenario, already a few scenario, right? Then next scenario is, kalau kamu perasan pula, kalau kamu tengok dalam design equation ada minus RA. Okay, so minus RA kita faham ada rate law yang berlainan. Then you realize in this rate law, kita ada CA, CB kan? Kita ada CA, CB. Okay, so sekarang we have to think also CA, CB in your rate law tu can be derived differently. Remember I taught you in chapter 3, the concentration of A, concentration of B of your reactant can be expressed differently because it depends on the phase. Are we talking about gas phase ke liquid phase? So kalau kamu ingat, kalau batch reactor, the concentration expressed the same, liquid atau gas. Batch reactor sama je concentration dia kita express. However, kalau flow reactor, kalau liquid, okay, and gas are expressed different way. Ataupun kalau kamu ingat saya kata express concentration untuk batch dan liquid flow adalah sama. Batch, liquid flow, the concentration are expressed the same. The only difference is actually flow gas. Flow gas, only your concentration is expressed a different way. Kan saya ajar kamu yang panjang-panjang equation tu, that one is to address for liquid flow system gas phase, meaning PFR gas, CSTR gas. Cara expression dia dah jadi lain, derivation dia pun dah jadi berlainan. Okay, so apa beza dia? Okay, kalau kamu tengok di sini, you can see from this diagram a clear concept of how the concentrations are different. Okay, contohnya kalau kamu tengok batch system, okay, so batch regardless liquid atau gas, okay, concentration dia kita express CA sama dengan CA0 in bracket 1 minus X, CB equals to CA0 in bracket theta B minus B per AX. This one is what we learned dah sebelum ni. Okay. So kalau kamu perasan, look at flow system liquid. Flow system liquid kamu tengok sama kan, kita express CA sama dengan CA0 in bracket 1 minus X. CB pun sama dengan CA0 theta B minus B per AX. Okay, so maknanya kalau CA, CB, liquid flow and batch both phases pun kita express the same way. Right, tu sama. Okay. Yang berbeza adalah untuk case gas phase flow reactors or flow system of which CA sekarang sama dengan CA0 1 minus X per 1 plus epsilon X. Okay, so at this stage, yang saya akan ajar sampai stage today, kita akan address only reactor which doesn't have change of temperature dengan change of pressure. Means isobaric, isothermal. Sebab tu kalau kamu tengok, dia jadi Ca0 1 minus X per 1 plus epsilon X. Dia tak ada part yang P0 per P, T per T0 tu tak ada lagi. Sebab kita masih address tak ada perubahan tekanan, tak ada perubahan suhu. Okay, so until this stage, until today saya akan ajar kamu tak ada part P0 per P, T per T0. Sebab kita assume yang kita akan design waktu sekarang ni masih lagi isothermal, isobaric. But later on, probably not today punya lecture, next week punya lecture, kita akan address pula kalau ada perubahan tekanan dalam sistem kamu, dalam kamu punya reactor. Dan dalam chapter 6, kita akan address pula kalau ada perubahan suhu. Okay, so you have to really understand equation yang saya ajar ni, dia akan berubah ikut certain situation. So you have to really remember, hari ni equation ni jadi macam ni. Tapi later on bila saya ajar kamu ada perubahan tekanan, ada tambah sikit lagi part. Dan chapter 6, our teacher you tambah lagi sikit part. So you have to really understand equation ni akan ada banyak-banyak version and you have to really understand which version applicable to what situation. Okay, so next I will continue for CB pula. So you tengok CB kita dah express lain because CB now become Ca0 theta B minus B per AX per 1 plus epsilon X. Actually, the only difference dalam concentration dia, kalau batch dengan liquid flow, yang pembawah tu tak ada. Tetapi kalau gas flow system, you see ada pembawah yang 1 plus epsilon X tu. Itu beza dia kalau kita ada gas phase flow system. Okay, so if you forget kenapa, as I explained in chapter 3, is purely because volume kalau batch reactor, volume reactor inlet outlet tetap sama. Okay. Kalau gas flow, liquid flow system, kita assume juga, bukan kita assume, technically, theoretically, volumetric flow rate untuk liquid pun tak berubah. Means inlet dengan outlet volumetric flow rate for liquid flow system is the same. However, flow system gas, inlet outlet volumetric flow rate is not equal anymore. Sebab tu kita ada correlation dia. We have an equation that correlates yang kata outlet volumetric flow rate sama dengan inlet epsilon equals to epsilon naught in bracket 1 plus epsilon X, okay, P naught per P, T per T naught. So again, I repeat, if you wonder kenapa P naught per P, T per T naught tu hilang, sebab at this stage kita assume dulu we are talking about isothermal isobaric reactor. Nanti a bit more later in chapter 4 kita akan address pula part perubahan tekanan. Chapter 6 kita akan address part perubahan suhu as well. Okay, so now you have learned basically apa yang saya terang ni you have learned in chapter 1, chapter 2, chapter 3. Okay, so now what we're going to do, we're going to combine all these three into the equation to develop the final design equation. So design equation sebelum ni hanya general. Okay, sekarang kita dah nak solve the complete design equation for us to find the either volume ke atau reaction time depending on the reactor. Okay, now before I go more, okay, if you realize juga, okay, let me go in this. Kalau kamu tengok design equation ketiga-tiga reactor ni, you realize batch reactor dengan part flow reactor, PFR, you have the integral part kan, ada part pengamiran kan. So kamu tengok kita kena solve basically the integral equation. Okay, so kalau dalam mathematics, when you take your mathematics course, you have to learn kan nak solve integral dia. Ada juga formula, or sometimes kamu kena ingat macam mana kamu nak solve pengamiran. Okay, so pengamiran tu biasanya dah ada formula. Okay, since in our reaction engineering pun, you can see that in order to solve the equation, kita kena solve part integral. The pengamiran part we have to solve. Okay, so to make it simple atau simplify it for you, dia dah ada the list of formulation dan solution dia terus. Means kamu dah tak payah crack your head macam mana saya nak solve pengamiran ni. Kita dah berikan dah kamu a list of formulation di mana pengamiran tu apakah penyelesaian dia dah diberi dalam list ini, list of integral formulation. Okay, so we will use this list of integral formulation, kalau kamu boleh tengok belah kiri pengamiran kan, belah kanan tu adalah solution dia terus. Contohnya katakan you want to integrate from 0 to x dx per 1 minus x. The very first one, you can see dia punya solution is ln 1 per 1 minus x. So itu solution kalau pengamiran dia dalam bentuk itu. Okay, second example, let's say you see the third one. So third one, let's say you're integrating from 0 to x dx per bracket 1 minus x square. Let's say kamu nak solve this integral equation. Penyelesaian dia dah diberi. The solution is given as x per 1 minus x. So you don't have to think anymore how to solve the integral. The integral solution has been given to you. However, the most important part is kamu kena faham there's a lot of solution, there's a lot of integral formulation kan, 1, 2, 3, 4, 5, 6, 7, 8. So you should be able to find out ataupun tengok solution mana, memenuhi integral mana yang kamu nak solve. So kadang kalau kamu tengok integral yang salah, then kamu akan solve salah lah. Okay, but for your case, not really a worry because it's an open book. I will do open book. It's an online test. Meaning you can always refer to the notes. Means kamu boleh terus refer saja formula yang last kali dah terus tahu. Tetapi as I told you, it's also important to know how it is derived supaya kamu faham dan lebih senang untuk kamu tahu which equation to be used. So I will show you how we derive using this integral formulation. Okay, now let me start first with batch reactor. So you must understand in this chapter 4, we are going to derive at least 30 to 40 equation or actually even more than that. So you kena faham kenapa sampai 30-40 equation dan kenapa equation ni berbeza. The most important part is not memorizing but understanding why kita ada sampai 30 kepada 40 equation dan macam mana nak tahu which equation is to be used. Okay, so that's what you're going to do in chapter 4. Right, so kita start first dengan batch reactor. Okay, so Miss katakan sekarang in your question or in your work or in your mini project, kamu nak design batch reactor. So you have to understand first, okay, kita nak buat sekarang batch reactor. Right, so why is it important kita nak design batch reactor? So as I told you in chapter 1, introductory, memang dalam case big scale production, we don't usually use batch reactor because we already learn batch reactor ni dia ada a long batch time, dia ada the only certain amount can be processed at one time, so it's not that efficient. However, as I also told you, batch reactor is an integral part in any reaction engineering because if you have a new reactions, okay, ataupun let's say you modify some part of your reaction or sometimes maybe you add catalyst or you change catalyst, okay, kamu pun tahu kan bila kita tukar catalyst, rate law akan berubah. Rate law akan berubah, design equation pun akan berubah. So, any changes in your system or in your reaction, you have to do back all the calculation. So, when this occurs, usually kita akan start dulu dengan batch reactor. Sebab, like I told you, kalau kita tukar raw material pun, kita tukar suhu ke, kita tukar catalyst ke, rate law dia mungkin akan berubah. Because you change something, the mechanism of the reaction may change. So, rate law berubah, design equation pun berubah. So, in order to establish this, kamu tak boleh buat kat reaktor yang besar. Kamu kena always start with a batch reactor to establish all this information. So that's why in the plan, kalau dia nak start dengan pilot scale, dia mesti start dengan batch reactor. Dia dah make sure semua dah optimize, semua variables dah okay, dia dah sure, baru dia akan upscale kepada flow system ataupun kita panggil continuous system. Okay. So what is important in the batch reactor? Normally dia nak establish either reaction time, dia nak tahu berapa lama masa tindak balas tu, ataupun dia nak tahu reaction rate constant K. Serta dia pun nak tahu K juga. So there are few things that they can know by conducting the experiment in a batch reactor. So that's what we're going to do juga. Kita derive equation, kita akan guna information tu untuk mencari apa dia bergantunglah kepada equation tu. Then in the real application, this information can then be used to upscale into a continuous system or we call it a flow system lah. Means kamu nak upscale kepada PFR ke, kamu nak upscale kepada CSTR ke, nak upscale kepada catalytic reactor ke, you must first start with batch reactor first. Okay. So this is how you derive the equation. Okay, so memang nampak macam panjang sangat. Okay, but I will explain one by one. Kenapa kita ada banyak sangat equation. Okay, now what we're going to do now is we're going to derive for first batch reactor. We're going to derive for both phases, gas dengan liquid. Kan saya kata sebab untuk case batch reactor, gas dengan liquid takkan berbeza sebab concentration dia masih sama. Okay, so we're going to do for batch reactor first. Okay, so I'm going to explain one by one combination dia, then you understand better. Okay, so since kita nak design untuk batch reactor, okay, so we will start with the batch reactor punya design equation lah sebab kita nak design untuk batch reactor, right? So design equation for batch reactor is equal reaction time. Kalau batch reactor, reaction time. CSTR, PFR, we will talk about volume. Okay, so the batch reactor reaction time, T batch, equals to NA0, okay, integrating from 0x dx per minus RAV. Okay, so kenapa 0 to x? Sebab batch reactor, satu reactor, dia will convert from zero conversion to the final conversion, your desired conversion. Then minus RA, kamu tahulah rate of reaction kan, rate of disappearance of A. V is the volume of the reactor which you have learned previously. Okay, then next step. Okay, now because, okay, when kamu tengok ada part pengamiran ni, kamu kena faham, this is also important for for other chapter as well. Dia adalah dx per minus RAV. Okay, so disebabkan the volume of the reactor will not be affected by the change of conversion. Kan sebab volume reactor tak kisah pun conversion dia 20% ke, 40% ke, 100% ke, volume reactor tu masih sama. Okay. Hence, I can take out the volume from the integral part of the equation. Dia keluar daripada part yang integral tu. So sekarang dia menjadi Na0 per volume reactor. So konsep pengamiran ni, okay, dia adalah anything yang akan berubah sebab dia pengamiran terhadap X. Dx tu means it will be integrated towards X. So any variables yang takkan affected by X ataupun takkan affected by the change of X, you can take out from the integral part. So itu saya keluarkan V, saya keluarkan keluar daripada kurungan pengamiran. So dia menjadi Na0 per V. Okay. Dan satu lagi part pula. Tadi mathematics, so kamu kena tengok macam mana connection between mathematics and chemical engineering. So next one pula, sebab volume reactor, kalau batch reactor, volume reactor tak berubah. Kan, maksudnya inlet to outlet reactor volume will not change in the reaction. The reactor tak shrink, takkan expand. So instead of writing volume, saya tulis sebagai inlet volume reactor, V0. Okay, so kenapa saya jadikan daripada V kepada V0 is because kat atas kan ada Na0. So kalau atas kat Na0, bawah ada V0, I can divide it becomes Ca0. So sekarang kita dah jadikan sekarang dalam bentuk Ca0. Okay. Integral part tu masih 0x dx per minus RA. Means kita akan evaluate minus RA terhadap x. Okay, so that's the first part. Now apa kita buat? Kita dah modify design equation batch reactor. So kita bukan sebarangan modify. Kita modify the design equation for the batch reactor dengan assumption that volume reactor ni takkan berubah inlet dan outlet. So now the design equation becomes Ca0 integrating 0x dx per minus RA. Done. Okay. Now next part. Minus RA pula. Kalau kamu perasan, kenapa kita tak boleh tinggal sebagai minus RA sahaja? Sebab we are integrating towards X. Tapi minus RA itu tak ada X kan? Minus RA is rate of reaction. There's no X in, kan tak ada max. Dan masih lagi tak ada X dalam part pengamiran tu. Walaupun kita nak kamir terhadap X. Therefore, we express the rate law. Kita dah belajar pasal rate law kan? Kita dah belajar pasal expression of rate law. So sekarang kita kena address pula. Minus RA ni kan, I teach you, we got minus RA equals to KCA. We got minus RA equals to KCA square. We got minus RA equals to KCA CB. As well as yang reversible kita tak touch lagi. Kita touch yang irreversible dahulu. So now kita kena buat untuk senario pertama, the first situation of which let's say your rate law minus RA tu equals to KCA, ataupun we can say, katakan for that reaction, it is first order with respect to A. Okay, sekarang kita ganti dah. Kita tak letak minus RA, kita gantikan minus RA equals to KCA. Maknanya katakan soalan tu kata ini adalah batch reactor, rate law dia is first order with respect to A. So it become minus RA equals to KCA. Okay, next. Walaupun tadi saya kata kita tak boleh kamikan terhadap minus RA sebab kita tak ada X, right? Lepas tu saya kata sekarang kita gantikan pula. Katakan rate law kita adalah minus RA equals to KCA. However, kita masih tak ada X lagi. Kan KCA itu tak ada X. Tetapi we have learned juga in chapter 3, we can express CA in the form of X. Sebab kita tahu kalau liquid and gas batch reactor, okay, CA sama dengan CA0 in bracket 1 minus X. This one kita dah belajar dalam chapter 3. Kita dah belajar nak express concentration. CA sama dengan CA0 in bracket 1 minus X. So now you see, saya dah ada X. Okay, macam mana X saya datang? X saya datang daripada CA. CA saya datang daripada mana? CA saya datang daripada minus RA. Minus RA itu datang daripada mana? Datang daripada design equation. So now you can see, I will now have to combine design equation, combine dengan rate law, combine dengan CA, concentration. So how do we do this? Okay, so we start with the first rate law. Kita start dengan design equation. Okay, reaction time equals to T batch to reaction time of a batch reactor equals to CA0 integrating 0x dx per minus RA. That is our starting point. Then kita replace, katakan in our question or in our reaction, it is first order with respect to A. As this example, we can replace minus RA with KCA. Sekarang ada dengan KCA. Lepas tu, as I told you, at this integral part, at the second step, kita masih tak boleh integrate sebab kita tak ada X. You want to integrate towards X, only kamu kena ada X dalam integral tu baru kita boleh kamikan. Kamu tak boleh kamikan K, kamu tak boleh kamikan CA terhadap X. Kamu hanya boleh kamikan X terhadap X. So what happened? I replace my CA with, just now that we explained dah kan, CA sama dengan CA0 in bracket 1 minus X. So step ketiga dia dah menjadi K CA0 in bracket 1 minus X. So you see at third stage sekarang saya baru ada X. However, at this part, dah kamu kena ingat satu lagi mathematics punya rule, okay, ataupun chemical engineering is a combination. As I told you juga tadi, sebarang variables that got nothing to do with X, you can take out from the integral part sebab dia hanyalah pengamiran terhadap X. Sebarang variable lain yang tak berkaitan dengan X, you can take out for the integral part sebab dia takkan dikamirkan terhadap X. Means dalam contoh ni, I can take out K, I can take out CA0 from that integral part because they will not be integrated towards X. So the K and CA0 sekarang, saya dah bawa keluar. So kamu tengok tadi asal ada satu CA0 di luar kan? So CA0 divided dengan the K and CA0 yang saya dah bawa keluar. So become CA0 per K CA0 integrating 0 to X dx per 1 minus X. So sekarang kamu tengok variable that got nothing to do with X dah bawa keluar. Dalam part pengamiran tu hanya tinggal X sahaja ataupun dalam bentuk 1 minus X. Okay. So, yang part CA0 per K CA0, kamu boleh tengok I can cancel 1 CA0 at the top, 1 CA0 at the bottom. So, dah boleh cancel kan? Sebab satu atas, satu bawah, I can cancel. So, I'm left with 1 per K. So, bahagian luar tu tinggal 1 per K. So, kita sekarang tinggal yang part pengamiran ni kan? Part pengamiran ni, okay. That as told you, kita dah diberi list of formulation. Tadi list yang paling panjang yang 8 formula tu, kita dah diberi the list. Okay. So the list says kalau kita nak kamirkan from 0 to X, dx per 1 minus X, this part of pengamiran, solution dia ataupun penyelesaian dia adalah ln in bracket 1 per 1 minus X. Means you don't have to crack your head nak selesaikan pengamiran ni. sebenarnya penyelesaian ni dah diberi. The solution is already given. If I want to integrate this, I want to integrate 1 per 1 minus x towards dx. The solution is ln 1 per 1 minus x. So solution yang ni saya copy sahaja masuk and I combine dengan tadi 1 per k. So sekarang kita dah dapat the final equation that correlates the reaction time of a batch reactor equals to 1 per k ln in bracket 1 per 1 minus x. Maksudnya, kalau kamu nak cari reaction time, okay, nak cari reaction time dalam batch reactor kamu tahu k, kamu tahu conversion x, you can find already the reaction time. Okay. Ataupun vice versa, katakan kamu dah set reaction time. Kamu dah tahu apa conversion dia, x dia, kamu nak cari k pun boleh. Ataupun katakan kamu tahu reaction time, kamu tahu k, kamu nak cari conversion pun boleh by using this equation. However, kamu kena faham equation ni kalau kamu nak guna, they have to fulfill 3 important parameters or 3 important requirement. First, dia mesti batch reactor. Second, dia mesti rate law dia minus RA equals to KCA. Kalau dia KCA square, KCA CB dah tak boleh guna equation ni. Third, okay, dalam kes ni liquid atau gas pun tak apa, sama. Okay, so requirement ketiga tu tak kisah sangat sebab liquid atau gas pun dia punya requirement design dia masih sama. Why? Because concentration ni kita express sama, CA sama dengan CA0 in bracket 1 minus X untuk liquid atau gas. Sebab tu equation dia sama untuk liquid atau gas. Okay, so you have already derived the very first equation, tetapi equation ni as I told you must fulfill 3 requirement, batch reactor, rate law mesti minus RA KCA, and third dia adalah liquid atau gas. Okay, done for the very first equation. Now we go to the second equation. So kenapa sekarang second equation, apa yang berbeza dalam second equation adalah bila kita tukar rate law. The rest are still the same. Dia masih batch reactor, dia masih liquid atau gas. The only difference is now rate law dia minus RA equals to KCA square. Okay, so itu saja perbezaan dia. Tadi minus RA sama dengan KCA. Sekarang minus RA sama dengan KCA square. So, adakah berubah tak dia punya persamaan? Okay, let us investigate. Okay, so kita start terus dengan deriving the equation sebab design equation batch masih sama. I'm still designing a batch. It's just that now I change the rate law. Okay, so katakan design equation dia yang tadi kita dah belajar, batch reaction time for batch equals to CA0 integrating from 0 to X dx per minus RA. Okay, so then next part. Now, kenapa dia berubah? Sebab minus RA tadi was KCA, first order with respect to A. This situation now adalah bila rate law dia adalah second order with respect to A. So become KCA square. So minus RA kita replace dengan KCA square. Okay, so similar to the previous one, kalau kita nak kamikan terhadap X, we have to introduce X into the equation. Kita tak boleh kamikan K, kita tak boleh kamikan CA kuasa 2 terhadap X. Dia mesti X dikamilkan terhadap X. So happen kita tahu CA equals to CA0 1 minus X. This one liquid atau gas, concentration is still the same. CA equals to CA0 in bracket 1 minus X. However, now in our equation, it's no longer CA, it's CA power of 2. So kalau CA power of 2, if you learn mathematics, kalau belah kiri kuasa 2, belah kanan kesemuanya terpaksa kuasa 2 juga. Meaning, if it's CA square on my left, on my right will be CA0 square, 1 in bracket 1 minus X pun kena square. Both kena square. Kamu tak boleh just square CA0. Kamu tak boleh just square the 1 minus X. Both have to be squared. So now kamu tengok equation dia become K CA0 square in bracket 1 minus X square. So nampak pengambilan saya, instead of writing KCA, dia menjadi KCA0 kuasa 2 in bracket 1 minus x tutup bracket also kuasa 2. Okay, now when you reach this part, okay, apa yang berlaku is, again same concept. K and CA naught square will not be affected by x. Maksudnya, dia tak akan dikamikan terhadap x. So the K and CA naught square, I will take out from the integral part. Saya bawa keluar daripada part integral tu sebab dia tak akan dikamikan terhadap x. So dia akan menjadi CA naught per K CA naught square. Pembawah tu dah bawa keluar kan? So pengatas tadi ada CA naught. So CA naught per K CA naught square. So again, saya ada satu CA naught di atas, saya ada dua CA naught di bawah kan, CA naught square. I can only cancel one CA naught at the top and one CA naught at the bottom. Only one can be cancelled. So kita akan menjadi 1 per K CA naught. Part yang luar tu dah menjadi 1 per K CA naught because we only cancel one CA naught at the top, one CA naught at the bottom. Done. Okay. So, part pengambilan pula. Okay, so kalau mungkin kamu belajar dalam mathematics, maybe you will have to buka the kurungan, darab-darab baru solve. Okay, itu kalau mathematics. Tapi untuk reaction engineering ni kamu tak payah because dah diberi solution dia. For this integral, from 0 to x, 1 per 1 minus x, tutup bracket power of 2, if you want to integrate towards x, kamu dah tak payah nak selesaikan secara complicated. The solution dah diberi. Tadi saya beri list of formulation tu kan, so saya terus ambil, saya terus catch. Dia sebenarnya untuk integral ini, for this formula, the solution is x per 1 minus x. Kamu tengok solution dia dah berbeza kan, tadi yang sebelumnya, kamu integrate towards 1 per 1 minus x. So dia jadi ln x, ln 1 per 1 tolak x. Tetapi untuk yang part kedua ni, kita integrating 1 per bracket 1 minus x square. So kalau itu formula dia, solution dia x per 1 minus x. So naturally apa kamu buat? Combine saja balik. So combine solution ni, x per 1 minus x, combine di bawah, combine saja yang tadi yang kat luar tadi yang 1 per k CA naught. So now we derive the second equation. So what is this second equation? This second equation is to derive reaction time for batch reactor. Okay, but the second case is for when your rate law is now second order with respect to A. You can see, right? It's different, right? Macam tadi saya tengok, let me show you. Tadi first order lain kan? First order reaction time, batch reactor sama dengan 1 per K. Ln in bracket 1 per 1 minus X. This is first order. Now, yang kita baru belajar second order, dia dah menjadi reaction time for a batch reactor equals to 1 per K CA naught in bracket X per 1 minus X. So, kenapa dia berubah? Sebab rate law dah berubah, derivation dah berubah, final equation pun dah berubah. Okay, so meaning, katakan dalam soalan, dia ask you to find reaction time. So if you are given K, you are given CA naught, you are given X, you can find reaction time. Or let's say, dia nak kamu cari K. So dia beri kamu reaction time, dia beri kamu CA naught, dia beri kamu X, you find K. Or they can also ask you to find CA naught. They beri kamu reaction time, they give you K, they give you X. They ask you to find CA naught. Or they can give you reaction time, they give you K, they give you CA naught, you have to find X. So either way, kamu tahu kan kalau satu equation, contohnya equation ni, kamu ada 4 unknown kan, reaction time, K, CA naught, X. So you can find either one of the unknown asalkan the other 3 unknown is given to you. So soalan exam, soalan test pun sama. Mungkin tak semestinya saya suruh kamu cari reaction time. Mungkin I give you reaction time, I give you reaction rate constant K, I give you CA naught, initial concentration of A, I ask you to find X, something like that. Okay, so yang penting satu equation, katakan dalam equation ni ada 4 unknown, 3 harus diberi, kamu boleh cari yang keempat itu depending on the question, depending on the situation. Okay, so done on the second equation. Kita baru 2 equation. Now, we go to the third one. So kalau kamu perasan, equation dia jadi panjang. Nanti kemudian at the very last, bila kamu tengok yang PFR, equation dia panjang sangat and don't forget, kamu kena ganti nilai kat dalam dia. Pengiraan dia jadi kompleks sebab dah lah equation panjang. Then kamu kena apply equation dia. So that becomes a little bit of complex problem jugalah. Okay, now we go to the third one for batch reactor. Okay, so kenapa the third one? Kenapa dalam batch reactor ada third one? Sebab now kita tukar rate law lagi. So the previously was first order with respect to A, KCA. We did also KCA square, second order with respect to A. The third one, we are addressing when the rate law is minus RA equals to KCA CB. Meaning katakan if your reaction is first order with respect to A and first order with respect to B. So now equation pun jadi berlainan. So bayangkan, katakan dalam soalan, so far kamu dah belajar dua, saya akan ajar yang ketiga kan. So katakan kamu tengok rate law yang salah. Katakan soalan kata rate law dia minus RA KCA square. Okay, kamu tersalah tengok, kamu pergi tengok equation yang minus RA equals to KCA. Salahlah the entire question. So kamu kena tahu rate law yang berlainan, kamu dah kena tahu equation dia dah jadi berlainan, kamu kena betul-betul tengok equation mana fulfill what you want to find. Okay, so the last one, okay, minus RA equals to KCACB. So katakan dalam soalan dia kata the reaction is first order with respect to A, first order with respect to B. So rate law dia minus RA KCACB. Okay, so now concentration dia kita dah kena tambah satu lagi lah kan. Sebab sebelum ni we learn for CA sahaja because the rate law only involve CA. But now our third one involve dah CB. So kita dah kena derive juga concentration for B. So as I taught you in chapter 3, kalau B adalah reactant, this is the case when B adalah reactant, CB equals to CA0 in bracket theta B minus B per A X. Okay, theta B kamu dah pernah belajar kan? B per A pun kamu dah pernah belajar kan? Dia adalah the ratio of stoichiometric coefficient. Okay, now for this part, there is something that is exception ataupun special rule applied in this equation. What do I mean by that? Okay, kalau kamu tengok original equation untuk CB, dia adalah sama dengan CA0 theta B minus B per A X. B per A itu kan adalah ratio of stoichiometric coefficient. Okay, normally B per A ni tak semestinya satu kan, tak mestinya satu sebab ia bergantung kepada tindak balas. Certain tindak balas, katakan 1A bertindak balas dengan 2B. Hence the B per A becomes 2. Ataupun let's say 2A reacting with 1B. So the B per A become 1 over 2, right? Okay, so it not necessarily 1. However, because in this equation, kita nak guna integral. Kita nak guna integral formula. Okay, so integral formula ni kan, as I told you, dia dah beri solution dia. Okay, disebabkan limitation formula ini. Again, because of the limitation of this integral formulation, B per A dalam equation tu harus menjadi 1. Because if it's not 1, kita dah tak boleh guna penyelesaian integral ini. Sebab tu, apabila B per A itu jadi 1, hence CB sekarang jadi equals to CA0 in bracket theta B minus X. Kita dah assume B per A itu adalah 1. Baru kita boleh guna integral formula yang kita dah ada. But don't worry, katakan dalam soalan test atau exam pun, saya dah make sure yang B per A itu adalah 1. Supaya kamu dah tak confused. Kenapa sebenarnya bukan 1, tapi dalam formulation tu kena jadikan 1. So, I will make sure B per A dalam soalan ke dalam test, dalam exam, B per A tu dah 1 supaya kamu dah tak confused, kamu terus tahu yang memang CB tu sama dengan CA0 in bracket theta B minus X. Sebab B per A tu adalah 1. However, as I told you, do remember, the limitation is just because of the integral. Kalau kita nak guna equation ni, B per A tu terpaksa menjadi 1, baru kita boleh guna. Kalau tak, you have to solve other way which is more complex. So that's the limitation of the equation. Okay, so done. Right, so then next. We do back the same thing. Kita combine design equation. We combine rate law. We combine concentration. But now it become a bit complex sebab dia dah ada CA, dia ada CB. Okay. So you see the last one. Okay. So integrating reaction time for batch reactor equals to CA naught. Integrating from 0 to X dx per by right minus RA kan. But the minus RA now is KCA CB. So kamu tengok equation kita dah berubah sebab tadi minus RA KCA. Second case KCA square. Third case KCA CB. So similarly again like previous one, I cannot integrate I cannot integrate KCA CB towards X because there are no X. So I will replace CA with CA naught in bracket 1 minus X. So my CA now become CA naught in bracket 1 minus X. Similarly, my CB is now, I convert it into CA naught in bracket theta B minus X. So sama, CA saya convert, CB pun saya convert dalam bentuk CA naught in bracket 1 minus X. Another one CA naught in bracket theta B minus X. So same concept. K and CA naught square. Kamu jangan lupa part bawah tu ada dua CA naught, right? Because one comes from CA, another one comes from CB. So the K CA naught square, I take out from the integral part again because they got nothing to do with the X. Ataupun dia takkan dikamilkan terhadap X. So it become, yang kat luar tadi ada CA naught, so CA naught divide by K CA naught square. So part luar tu dah bawa keluar jadi CA naught per K CA naught square. Dan part integral become integrating from 0 to X dx per 1 minus X bracket another bracket theta B minus X. Okay, so maybe kalau when you solve this in mathematics, you have to open the bracket. Kamu kena solve pengamiran kuadratik. Ataupun kamu mungkin terfikir, tapi doktor theta B pun tak ada kaitan dengan X kan? Kenapa kita tak bawa keluar? Sebab kita dah ada special formula untuk address pengamiran ni. Means, if kamu dah ada pengamiran 0 to X, dx per 1 minus X bracket, theta B minus X bracket, untuk formula ini dah ada penyelesaian dia. Sebab tu saya tak bawa keluar theta B ataupun saya tak darab, saya tak buka kurungan sebab dah ada penyelesaian dia. So the solution for this integral, the solution is given as 1 per theta B minus 1 ln in bracket theta B minus X per theta B in bracket 1 minus X. So kamu tengok for this integral, solution ni dah diberi. So saya just copy sahaja solution ini. Don't forget saya kena combine dengan part tadi yang CA naught per K CA naught square tu saya combinekan. Then sebab CA naught tu saya boleh cancel. I have one CA naught at the top. I have two CA naught at the bottom. I can cancel only one. So that's why dia jadi 1 per K CA naught. Dan saya combine dengan solution integral tu dalam equation. So now, kalau katakan your case reaction dia minus RA equals to KCA CB, the reaction time is now given as follows in the yellow box. Meaning, kalau kamu nak cari reaction time, kamu tahu K, kamu tahu CA naught, kamu tahu theta B, kamu tahu X, kamu boleh cari reaction time. Or vice versa. Maknanya sekarang dalam equation ni jadi more complex kan sebab kita kena ada berapa unknown. Reaction time, K, CA naught, theta B, X. Means 5 unknown ni, I can ask you any of the unknown dengan syarat lagi 4 unknown tu saya beri kamu. Contohnya katakan saya suruh kamu cari X. Means kamu kena, saya akan beri information, reaction time, K, CA naught, theta B. Kamu ada 4 information ni, kamu disuruh cari X. Ataupun vice versa. So theta B ni kamu tahu kan, kamu dah belajar kan, theta B adalah apa? Ratio of initial amount of B over A kan. Kamu dah tahu, kamu pun dah pernah tahu macam nak kira theta B. So done. So you can see equation become more complex sebab rate law dia pun dah jadi more complex. Okay. So you have learned 3 equation for batch reactor. So batch reactor reactor yang paling kurang equation adalah actually batch reactor. Okay. Batch reactor yang paling kurang equation, yang kompleks adalah sebenarnya untuk the continuous reactor, means CSTR dengan PFR. Okay. So Don't forget, okay, tapi saya rasa benda ni mungkin kamu tak ada masalah sangat, adalah kamu kena for your part as an open book test, you don't really have to worry about the derivation, honestly. Sebab you can terus refer untuk final equation. However, kamu kena tengok, kamu kena faham kenapa equation tu berbeza dan bila kita guna equation yang mana. So for batch reactor, not so bad because you only have 3 equation, 3 rate law, 3 equation. Kamu tak payah takut pasal the phase, liquid atau gas pun kita masih guna yang sama. So that's not really a problem, but it becomes a problem when kita buat untuk PFR. Okay, so now let us try one question first untuk batch reactor. So let's say kita tengok, kita buat soalan yang senang dulu. Okay, it says given a liquid phase reaction takes place in a batch reactor. So you take note. Okay, kamu dah kena faham bila sampai chapter 4, information pasal reactor tu penting. Ketika dia kata batch, kamu salah baca, kamu pergi tengok equation PFR. Salah dah. Kamu tengok equation CSTR. Salah dah. Means at the very first stage, kamu dah salah the entire question if you look at the wrong reactor. One. Second, dia kata reaction is first order with respect to A, first order with respect to B. So daripada information ni kamu dah kena tahu rate law dia apa. So the rate law is minus RA equals to KCA CB. So why KCA CB? Sebab dia first order with respect to A, first order with respect to B. So done. Kamu dah tahu dah. So kamu dah check. Kamu tengok dalam notes. Okay, first dia batch reactor. Kedua rate law dia KCA CB. Ketiga dia adalah liquid phase. Okay, kamu dah tahu dah 3 information ni. Kamu tengok equation mana yang memenuhi ketiga-tiga syarat ini. Okay, done. Next, dia beri kamu information nak solve equation dia lah. Okay, so kamu dah tahu at this stage, dia mesti sebenarnya rate law, design equation yang paling last yang kita belajar tadi, yang KCACB tu. Okay, next dia kata 60% inert reactant B, balance adalah A. So what is this sentence? Dia beri kita mole percent, or we can use this to find the mole fraction. However, 60 mole percent ni adalah mole fraction B. So YB not 0.6, hence YA not mestilah 0.4. 60% B, 40% A. So YB not 0.6, YA not 0.4. Normally kalau kamu diberi initial amount ni, mole fraction ke, mole percent ke, concentration ke, molar flow rate ke, ataupun number of moles ke, asalkan dia adalah initial amount, kamu tahu ni mesti nak cari theta B. So kamu tahu dia bagi initial fraction ni, kita akan guna untuk cari theta B. Okay, right, done. They give us reaction rate constant 0.1. Dia beri kita nilai K. Nilai K kita 0.1. So dalam soalan ni dia tak kata nilai K ni pada suhu apa. If they don't tell you at what temperature, as I told you, you can assume dia adalah pada suhu tindak balas. Okay, kan saya beritahu kamu nilai K change with temperature, right? But if they don't tell you at what temperature, you can safely assume dia adalah pada suhu tindak balas kamu, and means you don't have to find new K ke, you don't need to do anymore. Kamu dah terus guna nilai K ini. Next one. Initial concentration of A is 12 mole per dm cube. So what is this? This is Ca0. Dia dah beri kita pula. Ca0 12. Then dia kata 30% A converted. So apa ni? Ini adalah X. So dia beri kita YB0, YA0, K, Ca0 dan X. So they ask us to find reaction time. So dia bisa kita cari reaction time. Okay, so first step, okay, macam saya beritahu kamu tulislah dulu. Segala information tu kamu tulis dulu. Write in the form of the symbol. So this is a little bit of practice because I know you are not yet familiar with the symbol. Tapi kalau you try to get yourself familiar, kamu terus tulis dalam bentuk simbol supaya kamu terus faham apa variables yang kamu dah tahu, apa lagi variables yang kamu tak tahu. So most of the time saya perasan students yang dia ada masalah sebab dia tak boleh convert information dalam bentuk simbol. So bila dia tak boleh convert dengan betul, so dia tak sure apa yang dia tahu, apa yang dia tak tahu from the question. So first of all, like I told you, kalau dia beri kamu initial amount of the reactant, definitely untuk cari theta B. So kamu tahu theta B sama dengan dia bagi mole fraction, right? So initial mole fraction B over initial mole fraction A. So you get YB0 per YA0, you get 0.6 divided by 0.4, you get 1.5. Done. Okay, next. Dia beri kamu K, they give you CA0, they give you X. Okay. So if you are not sure where do you want to start, as I told you, kamu tengok dulu equation mana yang nak digunakan. Make sure you check these three. Reactor type, rate law, phase. So in this case, batch, rate law dia minus RA, KCACB. This is liquid phase. Okay. When you have these three information, there's only one equation yang akan fit kepada tiga-tiga ini, which is yang kita baru belajar, reaction time equals to 1 per K CA0 in bracket 1 per theta B minus 1 ln in bracket theta B minus X per theta B in bracket 1 minus X. So kalau kamu perasan in this equation, they want us to find reaction time. So kalau dia nak cari yang belah kiri, means yang belah kanan, all the unknowns tu dah ada nilai. Kamu kena make sure semua unknown tu ada nilai. Kalau kamu tengok ada lagi unknown yang tak ada nilai, kamu carilah. Means kamu tak akan dapat solve. One equation, satu sahaja unknown yang boleh ada, the rest kamu dah kena cari nilai. So kalau kamu tak ada nilai, kamu jangan solve. Dia takkan, it will never be solved possibly. Okay, so when you replace as I teach you, you will get the reaction time 1.9 second. Okay, this one, when you have extra time, please make sure you practice to press your calculator sebab dia ada bracket, sub bracket, main bracket, lagi satu main bracket. So I always realize student normally boleh ganti nilai yang betul, tetapi jawapan akhir tak semestinya akan betul sebab dia sometimes get confused. Sebab mathematics kamu kena fahamkan peranan bracket, sub bracket, main bracket. Kamu kena faham the aturan operasi when ada multiple, multiplication, division, addition, subtraction. So make sure you learn how to solve this properly. Try tengok kamu tekan calculator dapat tak jawapan akhir. Kamu kena ingat sebab on paper looks senang, tetapi press calculator, most of the time student will not get the final answer sebab tekan calculator salah. So you better make sure you practice when you have extra time sebab equation ni pun dah kompleks tapi kita akan belajar lagi kompleks shortly later. Okay, so done. We are done on batch reactor. Okay, so batch reactor ni sebenarnya tak susah sebab batch reactor hanya ada 3 equation. Okay, now I will introduce you to PFR. Okay, PFR ni lah jadi PFR dengan CSTR susah sebab banyak sangat equation. Kenapa? Banyak sangat version yang kita kena belajar. Okay, but I will go slowly first. Okay, so now I will go to PFR. Okay, so PFR ni kamu dah kena faham beza utama dia dengan batch. Kalau batch, dua-dua fasa pun cara expression dia sama. But for PFR and shortly later CSTR, fasa tu liquid atau gas, derivation dia dah jadi lain. Okay, kamu kena faham. Means bila kamu nak buat, kamu nak tengok equation, you have to really see these three things. Types of reactor, rate law, phase. Phase tu sangat penting, liquid atau gas sebab dia dah express berlainan. So kamu kena faham. First, kita kena buat untuk liquid. Liquid kita derive dah berlainan. Gas kita dah derive berlainan. That's why you have a lot of equations sebab liquid dan gas kita dah derive differently. Okay, tapi tak apa, I will go slowly again. And sebab dalam PFR, once more, PFR is integral equation. Okay, design equation PFR tu ada integral. Sekali lagi kita akan guna integral formulation ini. Okay, so similar to batch. Sebab dia ada integral, design equation dia ada part pengamiran. So kita akan apply balik formulation pengamiran ini tetapi it will be more complex and more comprehensive. So what do I mean by that? Okay, we start one by one. Okay, we start dengan liquid dahulu. Liquid is easier for us to express. So I start with liquid. So PFR, liquid phase. Kita ada 3 rate law tu kan. Kita ada minus RA KCA, minus RA KCA square, minus RA KCA CB. So again I repeat, we will have first situation adalah PFR, rate law PFR liquid yang of which kita divide lagi sebab kita ada rate law 3 yang berlainan. Okay, so I first start with liquid phase dahulu. Okay, so first design equation PFR adalah untuk cari volume. Kalau batch reaction time for PFR is for volume of the PFR. equals to Fa naught integrating 0x dx per minus Ra. So kalau kamu perasan beza kan, kalau tadi batch reactor, ni PFR kan, so volume Fa naught 0x dx per minus Re. So I start first with rate law yang paling senang, minus Ra equals to Kca. So means katakan rate law dia first order with respect to A, minus Ra Kca. Then third, dia adalah liquid phase. As I told you, kita baru nak buat liquid phase kan. So liquid phase, Ca sama dengan Ca naught 1 minus X. Okay, kita nak start dengan liquid phase. So concentration dia Ca sama dengan Ca naught 1 minus X. So maknanya untuk case ini yang kita tengah buat ni adalah untuk spesifik kepada PFR, first order reaction, liquid phase. So kalau soalan kamu tak memenuhi tiga-tiga syarat ni, equation ni dah tak valid. Dia mesti memenuhi ketiga-tiga syarat ni. PFR, KCA, liquid, only you can use this equation. So let me teach you how to derive. Okay. Sama. We start with the design equation. Volume PFR equals to Fa naught 0x dx per minus Ra. Okay, now kita dah tahu rate law kita minus Ra equals to Kca. So I replace minus Ra sama dengan Kca. So sama konsep macam batch. K dengan Ca saya tak boleh kamirkan terhadap X. I can only kamir something towards I can only integrate X towards X. So I must replace my Ca with Ca naught 1 minus X. So now dah jadi Kca naught in bracket 1 minus X. However, as I told you, K and Ca naught got nothing to do with X. They will not be integrated towards X. So I can take up my K and my Ca naught out of the bracket, out of the integral part. So it become, kat luar tu jadi Fa naught per Kca naught. Dah take out. So my integral part becomes 0 to X, integrating 1 per 1 minus X towards dx, towards X lah. Okay, so again, untuk part ni, you don't have to worry. Kita tengok je list of integral formula. Integral formula tu dah bagi solution. Kita tak payah fikir dah macam mana nak solve solution tu. It's already given. So it's given as ln in bracket 1 per 1 minus X. So saya just combine sahaja the ln 1 per 1 minus X. I combine with the Fa naught per Kca naught. So now saya dah dapat volume PFR sama dengan Fa naught per Kca naught ln 1 per 1 minus X. Maksudnya, katakan you want to find the volume, you are given information Fa naught, Kca naught, X, you can find volume, or vice versa. Let's say you are given volume Fa naught, K, Ca naught, kamu boleh cari X. Vice versa juga. Maknanya katakan dalam equation ni, satu unknown kamu disuruh cari, the rest information you are given. Okay, now, ini part yang sedikit kompleks pasal flow reactor. Okay, design final equation dia, ada version yang berlainan. Mesti kamu pening kan, kenapa ada version berlainan? Okay, because ia depends on information yang kamu ada. What do I mean by that? Okay, version pertama yang kamu baru belajar, yang I teach you how to derive, it is assumption that kalau nak cari volume of the PFR, saya kena tahu Fa naught, saya kena tahu K, saya kena tahu Ca naught, saya kena tahu X. Okay, now let's say kamu tak tahu Fa naught dan Ca naught. As I told you kan, kalau nak solve equation, satu equation kena ada satu saja unknown, yang lain kena tahu. Katakan dalam information tu, kamu tak tahu Fa naught dan Ca naught. However, let's say kamu tahu epsilon naught. Apa tu epsilon naught? Epsilon naught adalah volumetric flow rate. Fa naught molar flow rate, Ca naught concentration. Katakan kamu tak tahu molar flow rate A, initial molar flow rate of A, Fa naught. Kamu tak tahu initial concentration of A, Ca naught. So, kamu tak tahu dua ni, macam mana kita nak solve? But if you know volumetric flow rate, initial volumetric flow rate, you can also solve. Why? Because if you remember, Fa naught divide by CA0 is actually equals to inlet volumetric flow rate, your epsilon naught. Epsilon naught tu sama dengan FA0 per CA0. So, saya boleh replace FA0 per CA0 ni dengan epsilon naught. So now, equation saya dah jadi version kedua. Version kedua kata volume PFR sama dengan inlet volumetric flow rate epsilon naught divide by K ln in bracket 1 per 1 minus X. Maksudnya, kalau kamu tahu epsilon naught, kamu tahu K, kamu tahu X, boleh cari volume. Ataupun sama, kamu tahu volume, kamu tahu volumetric flow rate, initial volumetric flow rate, kamu tahu K, kamu boleh cari X, so on and so forth. So, version kedua ni adalah untuk kita kalau tak tahu FA0, CA0 tapi tahu epsilon naught pun kita boleh solve. Version kedua. Now, ada version ketiga. Kenapa ada version ketiga? Version pertama, version kedua cari volume. Version ketiga, kalau kita nak tahu dalam bentuk space-time. Do you remember I taught you in chapter 2 the concept of space-time? Space-time tu apa? Space-time is volume over initial volumetric flow rate, V over epsilon naught. Okay, I taught you in chapter 2. Sekarang kita kena correlate balik dengan chapter 2. Chapter 2 kita dah belajar juga pasal space-time. Space-time is volume over epsilon naught, volumetric flow rate. So, kalau kamu perasan, from the second version yang warna hijau ni, okay, kamu tengok belah kiri volume kan? Belah kanan, epsilon naught, K, ln 1/1 tolak X. This epsilon naught, this volumetric flow rate yang kat belah kanan, I can move to belah kiri. So, saya pindah ke belah kiri. Kamu tahu kan, kalau mathematic operation, kalau pindah kiri ke kanan, kanan ke kiri, yang pengatas akan jadi pembawah. The top will now become at the bottom. So, it become volume PFR over inlet volumetric flow rate, V per epsilon naught. So, V per epsilon naught tu apa? V per epsilon naught adalah space-time. So, now space-time tau, right? So, sekarang kita tahu tau for PFR. The tau for the PFR is 1 per K ln in bracket 1 per 1 minus X. Kenapa dah tak ada epsilon naught? Sebab epsilon naught kan dah pindah ke belah kiri, kita bahagikan dengan volume, dapat tau. So, now kamu ada version yang ketiga. So, version ketiga especially for space-time. Version pertama, kedua is for volume tetapi depends on diberi FA0 ke, diberi CA0 ke, diberi epsilon naught. Okay. So, then, however, kamu kena ingat ketiga-tiga equation dalam box ini is must be based on 3 syarat yang saya kata. PFR, first order reaction, liquid phase. Kalau salah satu syarat ni tak dipenuhi, ketiga-tiga equation ni tak valid dah. Okay, so that's the part that you have to understand. Memang tak payah bimbang pasal derivation. Tapi it become a problem bila student tak faham bila nak guna equation ni. So, ketiga-tiga equation ni kena penuhi 3 syarat. PFR, first order reaction, liquid. One, you tak fulfill this equation, all 3 are not valid anymore. Kamu kena cari equation yang lain. So, done on liquid phase. Okay, liquid phase first order. So, tengok first order liquid phase kamu dah belajar 3 kan? Okay, we go to the next one. Okay, next one is second order pula. Okay, so sekarang tadi kita buat PFR, liquid phase, first order. Now, I teach you for PFR, still liquid phase tapi sekarang dah second order reaction. Minus RA itu sama dengan KCA power of 2. So, you just remember tukar rate law, tukar equation. Tukar reactor, tukar equation. Tukar fasa, tukar equation. Okay, so now let us do for second order reaction. Okay, apa beza dia pula? Okay, so desired equation masih sama. The starting point is still the same sebab reactor masih sama kan? So, volume PFR equals to FA0 in bracket 0x dx per minus RA. Part ni masih sama. Just that, next, minus RA, I have to change. It is no longer KCA. This case is we consider if your reaction is second order with respect to A. So, part ni yang kadang-kadang kamu kena faham. Kenapa kadang-kadang I told you, kalau tukar reactant, kamu kena kira balik. Sebab when you tukar reactant, rate law dia akan berubah. Okay, ataupun kalau kamu tukar makin pun kadang-kadang dia punya reaction mechanism dah berubah. Rate law dah berubah lagi. So rate law sebarang perubah dalam tindak balas will change rate law, design equation dah berubah. Okay, so next, okay, so the minus RA become KCA power of 2 because that's my rate law. So same concept, CA dan K kena CA have to be converted into the form of X sebab kita nak kami terhadap X. So kita tahu liquid phase CA equals to CA0 in bracket 1 minus X. Hence CA square become CA0 square in bracket 1 minus X square as well. So kita square CA, CA0 pun square, in bracket 1 minus X pun kita kena squarekan. Then next step, the K CA0 square tak ada kaitan dengan X. So kita bawa keluar daripada part pengamiran. So kita bawa keluar tu bukan sembarangan sebab bila kita kamirkan terhadap X, kedua-dua ni tidak akan berubah terhadap X. So we take out, so at the outside it become FA0 per K CA0 square. Part pengamiran akan tinggal 0 to X dx per in bracket 1 minus X power of 2. So as I told you, kalau kamu buat matematik, mungkin kamu terpaksa buka kurungan, dia jadi kuadratik, kamu solve kuadratik tu for mathematics lah. Tapi for chemical engineering, reaction ni kamu dah diselamatkan. You don't have to go to the extent because terus diberi. Kalau pengamiran ni melibatkan dx per 1 minus X square tu, penyelesaian dia terus straight. X per 1 minus X. Okay, so kamu terus copy saja. So the X per 1 minus X, kamu combine dengan tadi yang part luar tu, FA0 per K CA0 square. So this formula you get is to find the volume of your PFR. Tu version pertama. So sama je konsep. Kamu tahu FA0, kamu tahu CA0, kamu tahu K, kamu tahu X, you can find the volume or vice versa. Okay, tak semestinya dalam setiap soalan kamu kena cari volume PFR. So macam sama juga macam real application kan. Katakan kamu kalau kamu nak cari volume reaktor yang baru, mungkin kamu akan guna equation ni untuk cari volume. Tapi mungkin dalam application, dalam real life application, mungkin kamu dah ada existing reactor. Katakan kamu ada existing reactor, kamu nak tukar just FA0, kamu nak tukar molar flow rate. Means kamu dah tahu volume, kamu tahu K, kamu tahu CA0, kamu tahu X, kamu nak tahu molar flow rate pun boleh digunakan. Equation masih sama. Okay, so next. Okay, next part. Sama je konsep macam tadi. For the first version, kita kena tahu FA0, kita kena tahu CA0. Okay, let's say kita tak tahu FA0. Okay, so instead kita tahu epsilon naught. So kita boleh tukar kepada version yang kedua. Version yang kedua sebab FA0 1 at the top divide by 1 CA0 at the bottom, you get epsilon naught. So saya dah ganti, instead dalam bentuk FA0 per CA0 square, sekarang jadi dalam bentuk epsilon naught per CA0 ada K. So bawah tu masih ada satu lagi CA0 sebab I can only cancel 1 CA0. FA0 at the top, cancel by 1 CA0 at the bottom, kan cancel lah. Divide 1 FA0 at the top, divide by 1 CA0 at the bottom, I get 1 epsilon naught. Satu lagi baki CA0 kat bawah tu masih ada. And then combine with K, and then the bracket X per 1 minus X. So now you get the second version. So apa beza dia? Version dia adalah version pertama ada FA0, version kedua tu adalah bentuk epsilon naught. So macam nak tahu version mana nak guna? Kamu kena tengok soalan lah. Soalan tu information apa yang diberi. So again kamu kena tengok version mana bergantung kepada information dalam soalan. So if you identify the wrong information, you may use the wrong equation, salahlah kamu punya jawapan. Okay, so the third version, kenapa the third version? Third version nak cari space-time. Sama konsep. Nak cari space-time pula. So kalau check space-time, just remember the epsilon naught on the right is transferred to the left. So jadi volume PFR divided by epsilon naught, you get the tau, the space-time for the PFR. So on the right hand side become 1 per K CA0 in bracket X per 1 minus X. So you must also remember, tadi pun kamu dah diraf space-time kan, tapi kamu perasan kamu diraf dua space-time yang berlainan kan. Kenapa? Previous one was for rate law dia KCA. This space-time dah berubah sebab this space-time is for rate law minus RA equals to KCA square. So same concept, These three equation is only and only applicable if your application soalan kamu ataupun masalah kamu fulfill these three. PFR, liquid phase minus RA KCA square. Salah satu tak fulfill, equation ni dah tak boleh digunakan. Dia tak boleh fulfill hanya satu, fulfill hanya dua, tak boleh. All three fulfill, you can use. One not fulfill, this equation is no longer applicable. Okay, so done, right? So tadi kamu dah buat batch 3. PFR first order 3. PFR second order liquid 3. So you have learned 9 equation already in like 1.5 hour. You already learn 9 equation. So as I told you, kamu tak payah memorize, tapi I keep repeating, kena betul-betul faham macam mana equation ni digunakan. Okay, next one. Okay, so now we do untuk the last rate law, minus RA equals to KCA CB. So kamu tengok equation dah jadi makin panjang kan, sebab sekarang kita address pula untuk minus RA KCA CB. So again, dia kena fulfill 3 untuk equation ni. PFR minus RA KCA CB liquid phase. Salah satu tak fulfill, ketiga-tiga ni pun again tak valid. Okay, so let me explain. Equation jadi makin panjang kan. Okay, so first of all, kita nak derive kan. So volume PFR equals to FA0 integrating 0 to X dx per KCA CB. Sebab rate law sekarang, the rate law is now KCA CB. Okay, then next. Same concept. Kita kena derive juga equation concentration kan. So CA equals to CA0 1 minus X for liquid. Okay, again, this is only for liquid. So for the case of liquid B, liquid for B, CB equals to CA0 in bracket theta B minus B per AX. So sama macam tadi yang batch. Okay, again, sebab we will use the same integral formula. And this integral formula, limitation dia adalah B per A tu mesti 1. Sebab kalau kamu tengok formula dia, kalau kamu perasan dalam formula dia, kalau yang saya tengah point ni, dia adalah 0 to X dx per 1 minus X dalam bracket theta B minus X. Maksudnya B per A tu mesti 1 baru kita boleh guna equation ini. Sebab tu kita terpaksa jadikan B per A tu 1. So that's why CB become CA0 theta B minus X. However, you must remember, dia hanya sebab untuk guna equation ini. Bukannya maksud semua case pun B per A adalah 1. Tidak. Just that for this equation, it has to be 1. But you don't have to worry. Okay, kamu just ingat saja yang dia adalah theta B minus B per AX. And I will make sure dalam equation persamaan kimia tu, B per A tu adalah 1. Ini dalam test ke, dalam exam ke, B per A tu dah 1. Supaya kamu dah tak payah bimbang, tak payah worry. Tapi equation kata B per A tu 1. Tapi saya tengok equation persamaan kimia saya, B per A tu bukan 1. So, I will not let that happen. You don't have to worry. So, B per A tu terus saja 1. Okay, done, right? Okay, now I combine balik. So, CA sama dengan CA0 in bracket 1 minus X. Then CB, I will replace with CA0 in bracket theta B minus X. So, saya replace CA, saya replace CB dalam bentuk CA0 1 minus X, CA0 theta B minus X. So, same concept. The K, the CA0 and another CA0, I take out from the integral part. So, dia jadi FA0 per K CA0 square. Integral part 0 to X dx per 1 minus X in bracket theta B minus X. So as I told you, kalau mathematics, you have to open bracket, so on and so forth. But we don't need to do this in reaction engineering because kita dah dapat solution dia. Kita dah diberi solution dia straight away. So it is actually 1 per theta B, ln in bracket theta B minus X, pembawa dia theta B in bracket 1 minus X. So this I combine dengan FA0 per KCA0 square. So when I combine, I get the rate font equation which is to find the volume PFR. So equation jadi lebih panjang kan? Kenapa berbeza? Sebab rate law dah berbeza. So first version sama macam konsep dia. First version tahu FA0, tahu K, tahu CA0, tahu theta B, tahu X. You can find the volume or vice versa. Okay, salah satu unknown kamu boleh cari, asalkan unknown yang lain kita tahu nilai dia. Okay, so the first version. Second version samalah. Second version katakan if kita tahu epsilon naught. If we know the inlet volumetric flow rate, you may use the second version, the green font. So green font tu beza dia just that, saya bahagikan satu FA0 di atas dengan satu C0 di bawah, I will get VR epsilon naught. So I get the second version. And similarly, I get the third version untuk mencari space time. So space time ni adalah untuk rate law minus RA, KCACB. I can find the space time for the this rate law. So it become tau PFR equals to 1 per KCA0 in the bracket the whole solution. So same concept. Why you got different volume? Why you got different space time? Purely because I changed my rate law. Okay, but all cases are for PFR liquid phase. So kamu dah belajar berapa? Kamu dah belajar 9 equation untuk PFR. Tambah lagi 3 tadi, kamu dah belajar 12 equation so far. Okay, so I hope yang penting kamu faham kenapa ada 12 equation yang kamu belajar so far. It's just purely because tukar reaktor, tukar rate law, tukar fasa. Tukar fasa belum lagi. Tukar fasa we will go next one when we change to phase. Okay, so we are done on PFR liquid phase. Okay, now I go to the more complex one ataupun basically equation yang paling panjang adalah melibatkan this situation. This situation is when is PFR gas phase. Tadi yang kita buat 9 equation PFR tu adalah liquid phase. Sekarang kita belajar lagi equation untuk gas phase PFR. So gas phase PFR kita kena address rate law yang berlainan juga. Okay, so let me do this slowly. How do we derive? Jadi ini panjang. Okay, so first, still the same concept. Design equation still the same. Volume PFR equals to FA0 in bracket 0x dx per minus RA. Still the same. Second, rate law. Kita try untuk case minus RA KCA. So maybe you think, tapi doktor dua ni kan sama macam tadi. Yes, it's the same. But benda yang ketiga yang menyebabkan dia berubah. Sebab sekarang kita buat gas phase. So kalau gas phase, tadi yang liquid kan? Liquid phase, concentration CA equals to CA0 in bracket 1 minus X. That was liquid. Tetapi gas dia tak macam tu. Gas dia jadi CA equals to CA0 1 minus X per 1 plus epsilon X. Disebabkan my concentration is expressed differently for gas phase flow reactor, menyebabkan final equation dah jadi lain. Sebab itu saja sebenarnya. And then derivation dia pun jadi a bit more complex. Okay, so how it happened? Okay, so same concept. Kita start balik dengan design equation. So FA0 in bracket integrating 0x dx per KCA. Minus RA saya dah jadi KCA. So sekarang saya tukar sebab CA saya akan tukar dalam bentuk CA0 dan X kan. So it become K tu masih ada, tapi CA sekarang jadi CA0 in bracket 1 minus X. Kalau liquid kamu stop macam tu kan, tapi gas kamu tambah pembawa dia 1 plus epsilon X. So sebab itu yang menjadi equation dia dah berlainan. And then kalau kamu tengok part ni kompleks kan, dia ada 3 layer, A per B per C. But if you remember I taught you, when you have A per B per C, the C goes to the top. A per B per C equals to AC per B. That's why this 1 plus epsilon X naik ke atas. So become 1 plus epsilon X ke atas. Kat bawah dia 1 minus X. Lepas tu, the K dan CA0 ni saya bawa keluar. Sebab dia dah tak ada kaitan dengan X. Saya bawa keluar K dengan CA0 ni daripada the integral part. So become FA0 per K CA0 integrating 0x 1 plus epsilon X per 1 minus X. So this part integral you have never seen before kan? Sebelum ni tak ada kamu jumpa yang part ni. However, sama case. Saya tengok balik list of formulation, dah ada solution untuk this integral. For this integration, okay, from 0 to x, 1 plus epsilon x per 1 minus x, the solution is 1 plus epsilon ln 1 per 1 minus x minus epsilon x. Epsilon kamu dah pernah belajar, I taught you before, right? Epsilon tu macam nak cari tutorial chapter 3 pun on Monday kita dah belajar macam nak cari epsilon tu. Okay, tapi kalau you don't remember, you forget, memang dia sebab dia ada a bit complex. Nanti tutorial kita akan discuss balik, ingatkan balik macam nak cari epsilon. So, kamu mesti kena ingat cara cari epsilon dalam chapter 3 tu masih digunakan dalam chapter 4. Okay, so come back to this. So, solution for this integral is combined with the FA0 and KCA0. So, saya combine yang depan, saya copy the integral solution, I get the final equation to find the volume PFR. So, again, this formula is specific for PFR. First order reaction, gas phase. So, kamu tengok, tadi kita dah pernah cari untuk first order PFR kan, tapi tu first order PFR liquid. This is first order PFR gas, dah lain equation dia. Sebab concentration dah lain. Concentration dah lain, express equation pun dah jadi lain. Okay. So, same concept. Nak cari volume ni, kamu kena tahu FA0, kena tahu K, kena tahu CA0, kena tahu epsilon, kena tahu X. Means, kamu kena cari dulu unknown yang lain untuk diselesaikan, only you can get the PFR volume. Then, same concept, ada version yang kedua. This green font version is because if you don't know FA0 dan CA0, but you are given epsilon naught, because dalam original equation, you have FA0 and bottom CA0 kan? So, FA0 divided with CA0 is actually epsilon naught. So, now we get the second version when we are given epsilon naught. The rest are still the same. So, again, nanti dalam tutorial, make sure you learn how to calculate. Sebab equation ni pun, student has the tendency to not able to get the final answer. Sebab, kamu tengok equation ni ada multiplication, ada ln, ada bracket, ada sub bracket, ada main bracket, ada division, ada subtraction. So, kamu betul-betul kena faham operation mathematics. Bracket, sub bracket, open bracket, addition, subtraction, multiplication, division. Kamu kena betul-betul faham ketamaan bila nak mengira ni. So, kalau kamu silap konsep, kamu tak ingat mana satu yang kena solve dulu, that's why the final answer you may not get accurately. Okay? So, tak apa, nanti tutorial kita akan practice. Okay, done. Then, last version samalah. Kalau I'm given, if I want to find space-time, nak cari space-time untuk PFR, first order, gas phase, pun kamu boleh cari. So, just bawa sahaja epsilon naught from right to left. So, you bring from right to left, dia dah jadi bahagi. So, volume bahagi dengan volumetric flow rate, you get space-time. So, space-time dia equals dengan 1 per K in bracket the whole entire solution. So, similar concept to the rest just now that you have learned. This three equation is only applicable if you have PFR, KCA, gas phase. Either one berubah, tiga-tiga ni equation dah tak boleh digunakan. Same concept yang tadi. Okay, so done. Okay, so the last one for today. Okay, so basically kamu dah belajar 3, 6, 9, 12 plus batch 3, kamu dah belajar 15 equation sebenarnya dalam masa 2 jam. Okay, so a lot, right? A lot. Later on Monday, kamu akan belajar lagi equation yang lain. Okay, last one for today. Kamu tengok, as I told you, ini equation yang paling panjang. It can never go any more longer than this. Okay, it can never go any more longer than this. Kecuali nanti kalau kita tambah a bit more, tapi tu dah taklah kompleks macam ni lah. Okay, so the last one is to address bila I have PFR, gas phase, rate law minus RA KCA square. Meaning, the reaction is second order with respect to A. So, kalau kamu perasan kenapa tak ada KCACB? Saya takkan ajar KCACB sebab Kalau kamu perasan, KCA square pun dah panjang ni. Kamu nampak equation dia panjang kan? Kalau tambah lagi KCA CB, equation dia 23 line kot. So, I don't cover KCA CB liquid phase, gas phase. I only cover KCA square. Because nak solve ni pun, it takes a lot of time and most of the time, final answer rarely sudah dapat betul final answer untuk yang ni sebab dia banyak sangat part dalam equation. Okay, so how do we address this? Okay, so again sama konsep, design equation sama, rate law yang berubah because minus RA equals to KCA square, and then concentration sebab dia adalah liquid gas phase. Okay, so become CA per CA naught 1 minus X per 1 plus epsilon X. So kita combine. So volume PFR equals to FA naught 0x dx per minus RA itu become KCA square. Then same concept. CA tu jadi kalau kita squarekan CA, yang belah kanan kita akan jadi CA naught square. 1 minus X square. 1 plus epsilon X pun kita squarekan. That's how we get this third part. Then sama concept. The K CA naught I take out from the integral part. So jadi FA naught per K CA naught square. Integral part yang kat bawah ni the last layer 1 plus epsilon X square ni goes to the top. So become 1 plus epsilon X bracket power of 2 divide by 1 minus X bracket power of 2. So same concept. This integral part luckily kita dah tahu solution dia ataupun the solution is given, tetapi kamu tengok betapa panjangnya solution dia. 2 epsilon in bracket 1 plus epsilon ln 1 minus X bracket plus epsilon square X plus 1 plus epsilon power of 2 multiply by X divide by 1 minus X. Ni yang paling panjang yang kamu tengok ni memang susah nak solve sebab dia ada multiplication, division, addition, subtraction. So part ni kamu betul-betul kena tahu mana satu yang kamu kena solve dulu. So this one is your mathematic punya knowledge. Bracket, sub-bracket, tambah, darab, tolak, bahagi. Which one comes first bila kamu nak solve? Okay, so sama je. You combine this formula, a solution dengan FA naught per KCA naught square yang tadi tu. So you get the first version to find volume. Then you get the second version yang the green font second version because instead of FA naught per CA naught square, we change into epsilon naught per KCA naught. Just kita bahagi satu FA naught di atas with one CA naught at the bottom, you get epsilon naught. And the third version is to find the space-time. So sama je konsep dia, space-time, the third version to find space-time. And again, these three equations is only applicable if you have PFR, rate law KCA square, gas phase. Salah satu berubah, equation ni dah tak valid for you to use. Okay, so PFR, you have learned basically 15 equation, tambah batch tadi 3 equation, 18 equation. Okay, so I told you right, you will learn 30 and 40 right, sebab kita belum touch lagi CSTR, kita belum touch lagi change of pressure, kita belum touch lagi change of temperature. That's why it can go to 30 or 40 equation. Okay, right? Okay, so next one, last one is let's try one question. Yang equation panjang-panjang ni kita try one question and tengok boleh tak kita solve equation dia. Okay, so this equation given an elementary gas phase reaction. So on that very one short sentence, kamu ada actually dua information yang penting. Yang kan kita ada 3 syarat kan? Jenis reaktor, rate law dengan concentration kan? So daripada satu ayat pendek ni kita dah tahu 2 benda dah. Apa dia? First dia kata gas phase. So kamu dah tahu this is gas phase reaction. Kamu dah kena faham. Okay, syarat pertama dia gas phase. Syarat kedua apa dia? Dia kata elementary. Kalau elementary means kamu dah boleh derive design equation dia. The design equation will be minus RA equals to KCA power of 2. Kenapa power of 2? Because elementary reaction order dia follow stoichiometric coefficient. The stoichiometric coefficient for A is 2. So minus RA equals to KCA power of 2. Second order with respect to A. Dua syarat dah penuhi. Kita dah tahu rate law, KCA square, kita tahu dia adalah gas phase. Okay, third dia information dia kata takes place in PFR. So kamu dah ada tiga syarat information yang kamu dah tahu. PFR, KCA square, gas phase. So kamu tengok equation tu, katakan kamu dah belajar ke semua equation kan. Kamu tengok pada notes kamu, okay, equation mana yang memenuhi ketiga-tiga ini. Okay, equation tu je yang betul. Equation lain semua tak boleh guna. Equation satu je. Akan ada satu sahaja equation yang memenuhi ketiga-tiga syarat ini. PFR, gas phase, second order reaction. Okay, done. Right. So sekarang kita tengok information lain yang kita tahu, yang dia nak kita cari kan. So dia kata constant temperature 500 Kelvin, constant pressure 8.2 atm. Okay, dia beri kita temperature, dia beri kita pressure. Okay, dia kata pure A is fed into the system. Okay, so dia kata pure A fed into the system, maknanya YA0 1. Okay, pure A maksudnya asalnya 100% A, so YA0 is 1. 500 Kelvin ni adalah apa? T0. Constant pressure ni 8.2 atm, P0. Okay, so kita tahu P0, kita tahu T0, kita tahu YA0. Okay, next. Given reaction rate constant 0.5. So K 0.5. Initial concentration of A 0.2. CA0 0.2. Initial flow rate 2.5 dm cube per second. Okay, so apa tu dm cube per second? Sebab flow rate ada dua kan, molar flow rate atau volumetric flow rate kan. Bila kamu tengok flow rate, kamu kena be very careful sebab flow rate ada dua, molar flow rate atau volumetric flow rate. In this case, is dm cube per second. Dm cube tu volume, second to time. Volume per time, volumetric flow rate. So this is initial volumetric flow rate, epsilon naught 2.5. Okay, next. Conversion 60%, 0.6. X is 0.6. They ask us to find the volume. Okay, so kita nak cari. Okay, so kita nak cari volume. Okay, so kalau kamu tengok information tu banyak sangat kan, kamu tak tahu macam nak proses kan, dia cara yang paling senang, kamu terus tengok dulu design equation yang kamu nak gunakan ataupun final equation that you need to use. Okay, so as I told you, you check which design equation yang fulfill ketiga-tiga syarat ini. PFR, gas phase, rate law second order. So hanya ada satu equation sebenarnya, okay, yang which is given as volume PFR equals to epsilon naught KCA naught in bracket, okay, 2 epsilon in bracket 1 plus epsilon ln 1 minus x plus epsilon square x 1 plus the so equation lah. Saya pun tak hafal, saya pun nak cakap pun panjang kan. Okay, kamu dah tahu ini equation kamu nak guna. So next step, dia kan nak cari volume. So nak cari volume, belah kiri is what we want to find. Means yang belah kanan kesemuanya mesti ada nilai. Kalau tak ada nilai, you cannot solve the equation. So kamu cari one by one information itu. Contohnya, first, inlet volumetric flow rate. So inlet volumetric flow rate dah diberi. Tadi kita tahu inlet volumetric flow rate 2.5. So kita settle dah epsilon naught. Second, K. K pun dah diberi. Reaction rate constant 0.5. Settle. Next, CA naught. CA naught pun diberi. Initial concentration 0.2. Done. So tengok dalam bracket pula. Pertama, epsilon. Okay, so epsilon, kalau kamu perasan, kita kena cari sendiri. You have learned dalam chapter 3, epsilon tu kita boleh cari. Epsilon tu sama dengan apa? Epsilon tu ada equation, ada sub-equation lagi kalau kamu ingat. So, part epsilon ni memang sedikit menyusahkan sebab kamu kena cari separately dahulu. But if you forget, let me refresh back. Epsilon ni sebenarnya sama dengan YA0 sigma. So, kita kena cari dulu epsilon tu sama dengan YA0 sigma. Apa tu YA0? YA0 is the initial mole fraction of A. Okay, so dalam kes soalan ni dia kata pure A initially means pada waktu asal dalam reaktor kamu initially is just A only. So YA0 is 1. Okay, done. What about sigma? If you forget, sigma ni ada lagi formula dia. So equation, sub-equation. Sigma ni adalah dia ada formula, and sigma is the ratio of the stoichiometric coefficient. Ratio dia kamu kena tambahkan ratio stoichiometric product minus ratio stoichiometric reactant. Dalam kes ni, you have only one product, one reactant. So it become B per A, positif B per A sebab B adalah produk. Positif B per A minus technically A per A. Sebab tu dia jadi 1. B per A tolak A per A. A per A tu 1. So jadi minus 1. Kenapa minus? Sebab A is a reactant. Okay. So B per A is 1 over 2. So 1 over 2 minus 1, you get your sigma negative 0.5. So as I told you, dia possible untuk dapat negatif. Tak apa pun. Okay, so sigma negative 0.5. You multiply dengan YA0 tadi yang 1, you get your epsilon. So epsilon is negative 0.5. Ingat yang volumetric flow rate tu adalah epsilon. This one is epsilon, different simbol, different pemahaman. Takut nanti kamu confused, kejap saya cakap epsilon. Epsilon tu volumetric flow rate. This one ni adalah epsilon, from Greek symbol yang berlainan. Okay, so you know YA0, you know your sigma, you will get your epsilon. Epsilon, as I told you, can be negative, can be positive, depending on your reaction. Kalau dapat negatif pun tak apa, dapat positif pun tak apa. Okay. So epsilon kamu dah ada kan? So kamu boleh ganti epsilon. Next, X. So X in the question is given as 60% kan? Dalam soalan kata X 60%, 0.6. So X 0.6. So yang menjadikan benda ni susah penyelesaian dia sebab kamu punya epsilon ni sekarang adalah negatif. So kamu bayangkan kamu nak kena ganti kat dalam ni, kamu have to be double, triple careful because my epsilon is now negative. So the rest you replace, you can find the volume of your PFR. So I would like you to challenge yourself. Nanti saya akan habiskan kelas ni in 1 or 2 minutes. So you have additional dalam 14 minit, 10 minit. Can you please try by yourself, calculate ni sampai dapat jawapan akhir. I want to see, and maybe you can ask your friend, or if you are together, you can try calculate, tengok kamu dapat tak jawapan akhir yang sama. I can tell you, kamu ada 29 orang kan? Kamu takkan semua dapat jawapan yang sama, mesti ada banyak-banyak version jawapan yang berlainan, tetapi akan hanya ada satu saja jawapan yang betul. Okay, so what I'm going to do is, I'm going to finish the class soon. Okay, for those yang berminat or you want to challenge yourself, you can try to solve this. And you give me the final, you type the final answer in the chat group. Nanti saya akan beri jawapan final, jawapan saya. Kita tengok siapa yang sebenarnya, bukan kita tengok lah, we see kamu kira betul ke atau tidak. Okay, so you just put in the chat group. If you have time, saya tak paksa. If you have time, nanti dalam 10 minutes tu you have time, you try to calculate by yourself. Dah ada pun semua nombor ni. Kamu kira, kamu bagi saya jawapan akhir untuk volume PFR ini. If there's enough answer, I will give you the final answer. We will see apakah beza jawapan sebenar dengan jawapan yang kamu beri. Tengok sama tak? Kalau sama, means you are on the right track. If tak sama, kamu check balik part mana yang kamu kira tak betul. Okay? So, that's all for today. Okay, tak ada dah kan? Habis. Okay. So that's all for today. So I will continue our lesson next Monday where I will continue habiskan dulu chapter 4 baru I go to tutorial. Okay, so for those who came late just now, I will do your test on week 7. So minggu ni minggu 5, next week week 6, I will cover on week 7 either during Monday class time or during the Wednesday time lah, during class time. Either way saya ambil class time, saya takkan ambil extra time kamu for the test. Okay, so that's all for today. Thank you everyone. So as I told you, if you got extra time, just try to solve. But before I begin, I will give a little bit of briefing lah of the things that you need to be aware of. So first of all, we will have, I will start first on the mini project. So by right lah, kalau you guys remember, the deadline submission for mini project is this Friday midnight. Okay, so the submission is on VLE. Make sure you compile into one PDF file and then you submit into VLE. Okay, however, I understand, I think I received email I think some of the students in reaction kena COVID. So if you have any of your members who has problem, regardless lah, not necessarily COVID, in any other matters that makes that you cannot submit the report this Friday, please inform me. Please inform me first. Get my permission dulu lah. If your members are not able to do so, means you cannot submit. Means the group cannot submit due to members or any whatsoever problem. Please inform me. Please get my agreement first. You may extend, but please inform me first kepada group-group yang kalau ada masalah sebab member dia have any other problems. Okay, so do inform me. Okay, jangan assume yang tak boleh extend ke, boleh je, tapi do inform me kepada group yang ada masalah untuk submit on time. Okay, so that's one lah for the mini project submission. Okay, Friday midnight on your VLE. That's one. Okay, then second, as you know, I already wrote in the Teams, we will have test. Okay, so test kita hari Rabu depan. So I do it during our tutorial time. Okay, so our tutorial time is 9:30 to 11:30. Okay, so the test time is actually 9:30 to 11. So what I'm going to do is I'm going to email all of you the questions through your UniKL student email. So make sure your student email is working. So I will email the questions to your student email. You download the questions. I will also attach the submission form. Okay, so you download the question, you answer on a white piece of paper, blank paper. Lepas dah jawab, snap picture or scan, compile it into PDF. Okay, compile it into PDF. Kalau bukan PDF susah sikit kadang-kadang. So make sure you dah ambil gambar ke, you dah scan, compile it into PDF. And then attach the submission page on the front, and then email it, submit it through VLE juga. So under VLE, I will put under test 1 submission. So the exam finish at 11. So after the test finish at 11. So after you are done everything, you're given another 30 minutes lah. Means you have until 11 to 11:30 to do all the compiling, so on and so forth. You're given 30 minutes for you to submit in your VLE. Okay, for the test. Again, do tell your friends if you cannot make it for the test, for any reasons, please contact me personally. Okay, so don't worry kalau betul-betul tak boleh sebab ada masalah kesihatan ke, ada masalah apa-apa ke. You know my style, you inform me. Okay, we will rearrange for you lah if you have problem. Okay, for the rest is still on Wednesday 9:30 AM. Okay, so saya pun tak nak keluar banyak sangat untuk test sebab I know that the short semester and I'm sure you got a lot of other tests. So I will cover from chapter 1 to chapter 3 sahaja. Okay, so what we done until chapter 3, that's all that I will cover. Okay, Rusha, your camera is switched on. Alright, okay. Okay, so make sure you download the question on time, so answer and then submit back lah. So that test is next Wednesday. Okay, so what I'm going to do is, okay, to facilitate and give you opportunity to study. So I know you got other tests because I did my course. So today is the class. Okay, today we have class, right? So Wednesday tutorial, I will not have any class. Okay, so you have that 2 hours to study. I give you opportunity to study as well as nak buat mini project. Sebab mini project submission Jumaat ni kan. So Rabu ni tutorial saya akan cancel, saya tak buat tutorial. Next Monday pun lecture I will cancel as well. So you have about 5 hours, bolehlah buat mini project and you can also take the time to study. Okay, so again I repeat first. So this Wednesday tutorial I will not do. Next Monday lecture pun saya takkan buat. So you got about 5 hours to do for your mini project and to do and to study for the test as well. And you have any problem for the mini project or you have any problem for the test, you please inform me accordingly. Okay. Tetapi, okay,
Doctor, sorry.
Yes, Amirul.
Yeah, the test on 6 April, right?
Yes, Wednesday during our tutorial time.
6 April lah.
Yes, minggu depan. Minggu depan Rabu. Welcome. Bukan Rabu ni Rabu minggu depan. Saya dah block dalam kalender. So please check your calendar. I already block mini project punya deadline. I already block the time for the test. So your things are already blocked accordingly in your calendar lah. Just that the test question, as I told you, please remember test question saya akan email kepada kamu punya student email. So during the test, you don't need to be on Teams. I do an open book test. You may refer to anything. The only thing that you cannot refer is your friends. Means tak boleh meniru jawapan kawan lah. Tu yang the only thing that you cannot do for my test is tak boleh meniru jawapan kawan. The rest you can do. You can open book, you can refer notes, you can refer anything, you can refer internet. The only thing you cannot refer is your answer, your friend's answer. Okay, so that's for the test. Right. However, I will need to take your time this Thursday sebab Thursday ni kan lab kan, but as I told you, I decided that we are not going to do physical lab, dah tak ada lab face to face. So instead, I will do online demonstration for the lab. Okay, so this Thursday, kan normally kita punya lab time 8:30 to 11:30, but you don't need to come, so you don't need to be on Teams so early. Just make sure that you are on Teams at 10 AM. So lab kita akan berlangsung daripada 10 AM. Okay, our lab will be from 10 AM to 11:30 AM. So just make sure you're on Teams. I already invite the calendar. I will do a live demonstration. So I will try my best, although actually you probably would not really see it clearly lah. I will try to use my iPad camera. I will get the technician to help. I will try to do the real operations of the lab, tapi mungkin setiap lab I can explain about maybe 30 minutes or maybe about 20 minutes, so on and so forth lah. But at least the most important is untuk kamu faham the reactor, sebab kalau kamu tak faham lab tu, nanti macam mana kan kamu nak buat lab report kan. My concern is saya takut yang part lab report lah yang kamu mungkin tak boleh buat kalau kamu tak faham lab. Okay, so but for that, let me do a little bit briefing on the lab part sebab saya dah mudahkan certain part because I realise actually 14 minggu untuk kamu students dengan a lot of courses actually is very challenging. So I decided I will simplify my laboratory part so that you don't have that much burden, that at least you, to be fair to you, you got time for other assessment. Okay, so saya just briefing sikit je pasal what is going to be different for our laboratory. Okay, so kejap Right, so this slide saya dah letak pun dalam our Teams as well as on your VLE. This slide is already there. Okay, you can refer to it. Just want to explain up what is going to be changed, what is changing in your lab part. Okay, lab assessment. Okay, so sebelum ni, kalau kamu ingat, kita ada lab report, kita ada pre-lab, kita ada psychomotor assessment. So saya rasa macam kesiankan kamu jugalah, I give too much sebab kamu pun ada mini project, and mini project tu pun sebenarnya dah susah. So what I'm going to do is, for the lab now, laboratory report tu masih biasalah, macam biasalah, I will explain later lah. Lab report macam biasa, you got 4 lab report. Yang pre-lab dengan psychomotor tu saya dah combine jadi satu online quiz terus. So means kamu dah tak payah buat yang pre-lab, yang banyak-banyak benda tu dah tak payah buat. Psychomotor pun tak payah. I'm just going to combine and do one online multiple choice punya quiz. So it's 1 hour quiz lah, 60 minit. I will open the quiz throughout the whole semester sampai minggu 14. I will try to post the question by this week. I try, if not next week. So you just masuk VLE, dalam VLE, you just do the online quiz 60 minit. Objektif je pun senang je. So that's all for your pre-lab dengan psychomotor assessment. So yang dulu saya beritahu kamu kena isi borang lah, kena buat apa, no longer applicable. You just do one online quiz. Online quiz tu will test you, will test you about laboratory practice, laboratory handling, a little bit on the laboratory as well, a little bit on the reaction engineering punya lab jugalah. So sebab tu kalau kamu jangan attempt awal sangat lah, you wait until you dah habis semua lab report, kamu dah betul-betul faham, mungkin towards the end of the semester, minggu 12, minggu 13, 14 baru kamu attempt quiz tu. So quiz tu actually lab kita 20 markah kan, the final grade is 20 marks. So 10 marks is actually from that online quiz, another 10 marks is from lab report. Okay, so I think this is quite fair lah, and the question untuk online quiz pun tak susah pun sebenarnya. It's just very basic question. It's just to help you to score, to at least get that 10 marks from your lab psychomotor and pre-lab. Okay, so that's the main change in our laboratory assessment. Okay, so next one. Right, so since that now kamu dah tak ada physical face-to-face lab, kamu mesti kena buat lab report. Okay, so apa yang saya buat is, I will give you, kita akan mula lab, Khamis ni saya akan buat lab demo. Sekali je lab demo, bukan setiap minggu. Today, this Thursday, I will do one lab demo, 10 o'clock, I will put in your calendar. So you attend that, it's considered as you dah attend lab. So that attendance is for the lab demo tu compulsory the attendance for the lab demo from your teams, on your teams is compulsory sebab tu menandakan yang you attend the laboratory session. Okay. However, don't worry, for those yang really wants to learn the laboratory face to face, tengoklah macam mana kalau end of the semester you got opportunity to come back to campus, you want to learn, okay, just text me, call me, I can always bring you for unofficial visit lah, okay, tapi tu kemudian lah bila kalau ada opportunity, okay. But for our lab, okay, you just attend this Thursday, dah kira kamu dah attend untuk laboratory session, okay. Then what I do, since kita minggu 6 kan, minggu 6 ni kita dah I already do lab demo, so I space out setiap 2 minggu kamu hantar satu lab report. So I think not too bad. And then so setiap saya dah bagi deadline lah, so maknanya minggu 8 first lab report, minggu 10, minggu 12, minggu 14. And then check juga, saya dah bagi schedule, saya dah bagi jadual, okay, group 1 lab report mana yang kamu kena hantar untuk minggu itu. So please make sure you check this, okay. Hopefully this doesn't burden you that much. Macam kamu tahu kalau style saya sebenarnya macam mini project pun sama. You don't need to do long. Okay, kamu tak payah tulis panjang-panjang. Bagi saya yang penting you hit the point, means okay, apa part kriteria yang kamu perlu ada, kamu jawab dah. Okay, so my style is short and straight to the point. So you don't need to worry yang kena tulis berpanjang-panjang page ke, tak payah. As long as you address what is needed, it's already more than enough for me. Okay, so for reaction for lab juga kepada mini project. Okay, so the same lab report pun submission on VLE. So group member kamu tolong kamu compile satu lab report, submit dalam VLE. So even lab pun I try to help you by putting 5%, normally 4. Okay, then I feel macam because the transition from 70 weeks to 40 weeks is very stressful to the student. I can really understand. I talk to some of your friend, the transition 17 kepada 14 dengan lab lagi, dengan mini project is very stressful. So this semester untuk ease up your transition, saya letak 5 orang, mini project pun 5 orang, lab report pun 5 orang. Lepas tu the last, kalau kamu tengok ada member kelima tu is actually I take from the FlexiLearn punya student. So I combine FlexiLearn punya student sekali. So to help you lah to ease up your burden on the lab report. Okay, so tak payah tulis lab report panjang-panjang. That's my advice to you guys. Tulis panjang pun sama je, maka tulis pendek pun sama je. So you hit the point what is needed in the lab report. And then you remember, right, lab report, setiap student dah ada part-part dia kan. So don't forget to rotate. For example, kalau minggu ni lab report 1 kamu student 1, okay, so next lab report kamu jadi student 2, so on and so forth. Sebab kalau kamu student 1 kamu hanya buat summary, kamu buat result. Kalau kamu student 2 kamu buat discussion, student 3, so on and so forth. So kamu kena rotate lah, means setiap lab report tu you will play a role, you will do one part of each of the lab report. So I think this way pun will help you a lot to save up your time and also to lessen your burden on the lab report. Okay, right. So then next, since you did not attend the lab physically, I already provided the experimental result, the sample of the result. So please use the sample of the experimental result for your lab report. Okay, so all the experimental result ni saya dah bagi, dah lengkap. So kamu check, kalau kamu eksperimen 1A, okay, tengok sample result eksperimen 1A. Kalau kamu 1B, check eksperimen 1B. So 2A, 2B, 3A, 3B, eksperimen 4. Okay, so please make sure you check. Saya dah tulis dalam schedule tadi, ketika group 1, eksperimen 1A. Kamu check lah sample result eksperimen 1A untuk buat lab report. Okay, so should be that's all. Okay, then saya tak explain selebihnya, tetapi I also prepare slide for you to help you to understand the calculation for the lab report. Sebab biasanya saya ajarkan, masa lab tu saya akan ajar kamu, but kita tak jumpa kan, tapi I already prepared all the slide to guide you how to do the calculation. Sebab biasanya part calculation ni memang a little bit memeningkan. So please make sure you check. I already sedia this slide dah ada dalam Teams dengan VLE. Please refer to this when you are doing the lab report, because I teach you how to do the calculation, macam mana nak plot graph, so on and so forth for each experiment. I already prepared for you. Okay, so hopefully this one also will help you to lessen your burden, and then kamu tak payahlah spend terlalu banyak masa untuk fikir macam mana nak buat lab report. Okay, alright, so that's all for the lab report. mini project and the test. So pada yang datang lambat tadi, again saya repeat, test Rabu depan, bukan Rabu ni, Rabu depan pagi. Mula-mula saya nak ingatkan nak buat Isnin, tapi Isnin kelas kita petang. Saya rasa macam Isnin tu kamu dah start puasa. Kalau tengah-tengah petang tu saya rasa mesti kamu dah layu. Kesian juga kalau 4.30 saya buat sampai 7. I'm sure you do not have the enough energy. So I decided tak apalah saya buat Rabu pagi dalam 9.30 lah Rabu pagi. So hopefully doing it morning will give you a better mood lah untuk sit for the test. Okay? So hopefully that also helps you in your test as well. And again, please tell your friends sebab saya rasa ada kawan kamu sekarang yang kena quarantine COVID ataupun ada yang kat quarantine center. So kalau kamu boleh pesan kat dia ke ataupun kamu boleh beritahu saya ke on behalf of your friend, please tell me supaya I can rearrange the test for those people yang tak boleh sit for the test. Okay, right. So done on the mini project. Okay, now I will continue on lecture chapter 4. But today punya lecture pun tak banyak. Kita nak just habiskan yang baki. Alright, and then tak apa, tutorial kita buat lepas sem break lah. Means Rabu ni saya tak kacau kamu, saya bagi kamu masuk untuk buat mini project. Khamis kamu attend lab sekejap, online lab. Isnin depan pun kamu free 3 jam, kamu boleh belajar untuk test saya. Dan Rabu tu kamu sit for the test. Okay, right, so I'm back to my lecture chapter 4. Okay, pada yang datang lambat lagi sekali saya ingatkan, test is only chapter 1 to chapter 3. So kalau saya masuk chapter 4 saya rasa susah sangat. Saya pun kesian juga. Tapi tak apa. Jadi chapter 4 I will include in the second test lah. Chapter 4, 5, 6 second test. Test 1 is only chapter 1, chapter 2, chapter 3. So kalau kamu nak tanya macam mana nak buat untuk test, kamu just make sure tutorial tu kamu jawab. Macam soalan tambahan yang saya bagi tu kamu jawab. And then make sure kamu betul-betul faham lah. So normally test 1 okay. Normally. Tapi kita tengok macam mana lah. We see how for this semester. Right, so I'm back to my lecture for chapter 4. Okay, so to recap back, kalau kamu ingat, you learn a lot of equation, right? You learn banyak equation. I think last week we covered like 21 equation. So today we cover a little bit more equation, tapi we are left with only one reactor. So last week you have done already a batch dengan PFR, and I'm sure you already got very confused sebab banyak sangat equation. Okay, so hari ni pun a little bit more equation, tapi tak apa. Nanti bila kamu naik sem break, sebab minggu ni minggu 6 kan, minggu depan minggu 7, lepas tu dah sem break. Okay, naik sem break baru kita buat tutorial, then kamu akan faham lebih baik. Tapi basically chapter 4 ni lah I told you dia banyak equation. Dia kan open book, macam test 1 pun saya buat open book. So you can just refer. Tapi of course lah kalau tak faham tu susah sebab kita ada banyak equation, right? So that will be the main challenge lah. Bila terlalu banyak equation, kita tak tahu macam mana nak guna. Okay, so today we will cover CSTR. Okay, kita ingatkan kita nak design equation dia kan. Okay, so why we have so many equation? Last week you learned 20 equation. Why we have so many equation? Because you know that dia ada certain criteria yang you have to fulfill. Satu kriteria berubah, equation pun dah berubah. So that was 3 main criteria. First is the type of reactor. Okay, are we designing batch? Are we designing PFR? Or are we designing CSTR? So for today, we're talking about CSTR. So benda pertama kamu kena check. Then second is kamu kena check liquid atau gas phase. So itu pun penting. Okay, kalau dia liquid, equation dah berlainan. Gas phase, equation dah berlainan. Means CSTR liquid lain dengan CSTR gas. Okay, second. Third criteria, rate law dia. You remember, right? Reaction, we got different rate law. Kita ada rate law first order with respect to A. Kita ada second order with respect to A. We also have rate law where is first order with respect to A, first order with respect to B. So kita ada minus RA equals to KCA, minus RA equals to KCA square, minus RA equals to KCA CB. Okay, so different rate law pun equation akan berlainan juga. So we have 3 criteria. So make sure you have to check these 3 accordingly. So katakan kalau equation kamu refer to doesn't fulfill all 3, definitely equation tu salah. So you must be very careful when we are looking at the equation. Tetapi the good thing about CSTR equation, design equation dia very easy. Dia yang tak ada dah pengamiran. Remember last week we learn kalau batch dengan PFR, we have the integral. So integral itulah part yang susah because we have to integrate the equation. CSTR ni tak payah integrate, okay? Because CSTR punya design equation tu dah memang linear, okay? So how do we elucidate or how do we design the equation, okay? So let us start very simple. Kita start dengan liquid sebab if you remember, liquid memang senang nak express. Yang susah adalah sebenarnya gas phase. Okay, so kita start dengan liquid. So, three things first. First, CSTR. So, you know CSTR, the design equation is to find the volume. So, the volume of CSTR equals to FA0x per minus RE. So, design equation dia is given as this. Okay, now we do when is the rate law is first order with respect to E. So maknanya katakan sekarang dalam tindak balas kita tu rate law dia minus RA equals to KCA. Okay, so untuk test minggu depan kamu dah kena faham lah apa tu rate law, apa maksud dia kalau kata first order, second order, so on and so forth. Okay, so sepanjang today punya kelas I will give you a little bit of hint, I will tell you apa yang penting kamu kena tahu. So dalam chapter 3 kita belajarkan pasal rate law, so by now you dah kena faham. Kalau katakan seorang kata first order with respect to E. Apa maksud dia? Maksud dia rate law dia minus RA tu sama dengan KCA. Power of 1. So power of 1, biasanya kita tak tulis the power of 1. That's why it become KCA. Okay. So next, kita akan write down the concentration. Concentration pun kamu dah belajar dalam chapter 3, right? Kita dah belajar cara express concentration untuk flow reactors. Kalau cakap pasal flow ni, PFR CSTR lah. Dan kamu kena ingatkan, dia ada liquid, dia ada gas. So kamu kena tengok, kalau liquid, concentration dia kita express as Ca equals to Ca0 in bracket 1 minus X. Okay, so honey liquid. Okay, kita express Ca equals to Ca0 in bracket 1 minus X. So what we do now? Kita combine 1, 2, 3. Okay, kita combine number 1, number 2, number 3. So we get volume CSTR equals to FA0X per our minus RA are replaced with KCA. Okay, dah replace dengan KCA. Okay, but you always remember, kita selalu akan evaluate in terms of conversion. Okay, kita mesti bercakap nanti dalam soalan test ke exam kamu tengok memang conversion tu akan ada lah. Information pasal conversion tu akan ada. Kecuali kalau disuruh kamu cari conversion. Kalau pengiraan lain, dia mesti will have X. So when this equation doesn't have X, that's why kita terbitkan balik Ca ni dalam bentuk Ca0 in bracket 1 minus X. So that's why we learn to express concentration. Sebab writing Ca, kita tak measure Ca. We always measure in terms of X and terms of Ca0. Okay, so become K Ca0 1 minus X. So done. So you can see the red part is basically you dah derive design equation to find the volume of a CSTR if the reaction is a first order with respect to A. Okay. However, okay, equation ingat macam PFR kan kita ada version yang berlainan of the design equation. So kenapa kita ada version yang berlainan? Sebab dia depends on information given to you. So for example, katakan you want to find the volume, you know FA0, you know X, you know K, you know Ca0, kamu boleh solve. Ingat kan kalau macam kamu nak solve any mathematics or any engineering questions yang melibatkan pengiraan, even for next week test, kamu kena tahu apa yang kamu nak cari. Okay, katakan kamu ada satu equation, you know what the unknowns that you want to find, the rest tu kamu dah kena cari dulu nilai dia. So means kalau unknown lain, the other unknowns, unless you can solve all the value, it's impossible for you to get the desired unknowns punya nilai. Okay, so make sure you tahu, okay, katakan you nak cari volume. Okay, katakanlah walaupun soalan chapter 4 takkan keluar, tapi katakan you want to find volume, so you know without FA0, without X, without K, without Ca0, I can never solve this problem. Okay, so that's one thing that you must really remember even next week when you're answering the task. However, let's say you are not given FA0 dan Ca0. Okay, so for those yang tak ingat, apa tu FA0? FA0 tu adalah initial molar flow rate of A. CA0 tu initial concentration of E. So maksudnya untuk next week test pun make sure kamu dah tahulah. Okay, kalau dia kata molar flow rate, apa simbol dia? Kalau kata concentration, apa simbol dia? Volumetric flow rate, apa simbol dia? Okay, number of moles, apa simbol dia? So that will be the biggest challenge for test 1 normally untuk students sebab I can understand baru belajar 7 minggu nak ingat semua simbol, and then of course I'm not the only course that you learn. You got many other courses that you learn. It's definitely definitely a challenging task lah. Okay, so but you have to somewhat get familiarized. Sebab tu kalau boleh tengok dalam contoh chapter 3 punya soalan, tengok tutorial, yang penting mesti faham. Kalau kamu faham, most likely okay je sebenarnya. Okay, so let's say kamu tak tahu FA0 dan CA0, or let's say you are not given FA0, you're not given CA0. However, you want to find the volume. Okay, but you know that FA0 and CA0 is correlated to inlet volumetric flow rate, epsilon naught. So ni pun kamu kena ingat lah perkaitan antara ketiga-tiga parameter ni. Volumetric flow rate, molar flow rate dengan concentration, which volumetric flow rate ni sebenarnya sama dengan FA0 per CA0, ataupun cara senang untuk kamu ingat bagi saya adalah kamu ingat FA0 tu sama dengan CA0 multiply by V0. Easier lah. Biasanya kita bahagi ni kita akan confuse tau nak mana satu pengatan mana ke bawah. So normally I will remember multiplication. So I remember FA0 tu sama dengan CA0 multiply with epsilon naught. Ataupun kalau nak tahu epsilon naught maka equals to FA0 per CA0. Okay, so now I can replace my FA0 at the top and the CA0 at the bottom. If I divide, I will get the epsilon naught. So sekarang saya dapat version kedua equation saya, which is epsilon naught X. Yang lain semua tak berubah. So epsilon naught X per K in bracket 1 minus X. So this also formula can be used to find the volume of your CSTR. So version pertama, version kedua, beza dia. Version pertama, if I know FA0, CA0. Version kedua, if I know epsilon naught, the volumetric flow rate. And then, similar to PFR, we can also use to find the space-time. So space-time chapter 3 kita dah belajar kan. Okay, to recap back. Chapter 3 kita dah belajar juga space-time, tau. Okay, kalau you see tau, tau is means space-time. Apa tu tau, space-time? So space-time is equals to volume reactor per inlet volumetric flow rate. V divided by epsilon naught is space-time. Kalau space velocity 1 per space-time. 1 per tau is space velocity. Kalau nak cakap pasal space-time itself is only volume per epsilon naught. Volume per inlet volumetric flow rate. Itu pun kamu kena ingat untuk test minggu depan. Definitely akan ada question about that. So you have to remember that. Okay, so correlated back to this, kita pun boleh cari space-time. So to find the space-time, if you realize on your left, you have volume. On your right, you do have 1 epsilon naught kan? Epsilon naught X per K in bracket 1 minus X. So the epsilon naught ni, if you realize from right, I can move to the left. So from right to the left. So at first it's at the top, but when you move to the left hand side, it become bottom. Dia akan jadi division. Okay, so you become volume over epsilon naught, volume over inlet volumetric flow rate. Okay, so this volume per inlet volumetric flow rate is actually our space-time. So that's why we get our space-time. So sekarang kita dah boleh cari space-time. So belah kiri dah dapat space-time. So what happens to belah kanan? So belah kanan akan tinggal X and divided by K in bracket 1 minus X. So now we had the third version of the equation, of which this is used to find space-time. So katakan kamu confused mana satu kita nak guna. It depends on the question. First, dia nak cari volume ke dia nak cari space-time? Katakan dia nak cari volume. Apa information dia beri? Do they give us FA0? Do they give us CA0? Kalau dia beri, you use the first version. Let's say they don't give. They give you inlet volumetric flow rate. You can use the second version. So that's how you differentiate. However, yang penting, all three equation hanya boleh digunakan if your questions or your reaction fulfill these three things. Dia mesti CSTR, dia mesti liquid phase, dia mesti rate law dia minus RA KCA. Kalau salah satu tak dipenuhi, tiga-tiga equation ni dah tak valid ataupun dah tak betul lah kalau kamu guna equation ni. Okay, so done for CSTR. Okay, sorry, CSTR first order. Right. But before I go further, there's something interesting or there's something additional about CSTR liquid phase ini. Okay, nanti dalam report pun kamu akan tengok benda ni. Okay, so for CSTR liquid phase, first order reaction yang tadi kita buat tu, minus RA sama dengan KCA tu, tadi kita derive kan? Kita dapat space time dia yang tadi kita buat equals to X per K in bracket 1 minus X. Okay, tadi yang first order kita derive the space time, we get this. Right. So what I do is, let's say I move my K, okay, reaction rate constant. Okay, so chapter 3 pun kita dah belajar kan reaction rate constant. Okay, don't forget apa tu reaction rate constant. Macam mana kita nak kira reaction rate constant? Kita akan guna Arrhenius equation. Make sure kamu practice. Macam mana kita nak guna Arrhenius tu, kamu practice. Okay, so the reaction rate constant tu, if saya move from right to left, right to left. Okay, when you move right to left, the K will go to the top, right? So K akan berpindah ke atas. Okay, so it become tau CSTR multiplied by K. Okay, so this tau CSTR K is what we call as a Dam Collar number. So today you learn another one more thing. You learn Dam Collar number. Okay, so maybe I think in engineering you have learned many types of number kan. Kalau sebelum ni mungkin you have belajar pasal Reynolds number. So for those yang, I think you have learned before Reynolds number. Reynolds number ni kamu ingat kan ada formula kan. Kamu kira formula dia density multiply with velocity diameter over viscosity if I'm not mistaken. Reynolds number tu kalau kamu ingat, kamu akan kira number dia. So this Reynolds number is used to predict the behavior of your flow. So kalau kamu ingat, kalau number Reynolds number kamu kira ni ikut formula, if below 2500, kita kata the flow, aliran liquid tu adalah laminar flow, ataupun maksud dia aliran flow tu adalah tak bergelora, laminar flow. However, if you calculate Reynolds number tu more than 2005, bukan, more than 4000, we call it as turbulent flow. Maksudnya, kamu boleh predict aliran cecair kamu tu akan aliran yang bergelora. So why do people do this type of prediction? Sebab ingat kan, contohnya kamu tahu kalau macam let's say we want to transport fluid in a pipeline, it's going to be a big pipeline and you cannot always monitor, tengok dalam pipeline aliran dia bergelora ke, aliran dia tenang ke, we cannot, right? We cannot use physical examination. Hence, kita guna this engineering number to tell us the prediction. Means katakan kalau saya kira Reynolds number saya 2000, most likely aliran fluid saya adalah aliran yang tak bergelora, aliran yang tenang. However, if it's above 4000, most likely aliran fluid saya adalah aliran yang bergelora. So why this is important? Because then I can manipulate. Sama ada saya nak kurangkan laju ataupun saya kurangkan density dia ataupun viscosity fluid dia. Saya boleh manipulate supaya make sure aliran kita tu tak nak aliran turbulent. Normally kita tak nak aliran flow yang turbulent sebab kalau turbulent pipeline you will have then additional problem lah, especially macam pressure, so on and so forth. Okay, so the story of it, why I tell you the story is because the number tu is used to predict phenomenon. That's what Reynolds number do. Reynolds number predict the flow phenomenon. Okay, in this case, in this reaction, we got Dam Collar number. So this Dam Collar number is also a number to predict phenomenon, a phenomenon, which is the conversion. Okay, apakah maksud dia? Maksud dia macam ni. Okay, let's say now, but dia ada syarat dia jugalah. Dia hanya khas untuk specific, hanya untuk if you use a CSTR first order liquid phase. So kalau kamu guna gas phase dah tak valid, kamu guna bukan first order dah tak valid, tak guna CSTR pun tak valid. Dia kena memenuhi ketiga-tiga ni. Okay. So Dam Collar number ni macam ni kita nak kira. Kalau kamu tengok equation is equals to tau K. Tau tu apa? Tau kan tadi kita belajar kan space time kan. So volume per inlet volumetric flow rate. Means kamu dah tahu volume reaktor kamu dah tahu. Mestilah kamu tahu kan berapa besar reaktor kamu. Inlet volumetric flow rate tu kamu boleh adjust. Okay, kamu tahu sebab kamu yang akan set inlet volumetric flow rate. So you kira your space time, you multiply with K. K tu reaction rate constant. So, as I told you, biasanya kalau reaction tu reaction yang common one, okay, you will know berapa nilai reaction rate constant tu. Sebab untuk tindak balas yang biasa, orang dah establish, orang dah cari sebenarnya berapa nilai K. So, you can know the value of the K. So, you calculate, okay, tau K. Okay, so when you calculate the value of the tau K, value tu akan indicate the conversion. Okay, katakanlah, okay, if your then column number kamu kira adalah 0.1 or lesser than 0.1. Kamu kira kamu dapat then column number tu means kamu kira tau volume per volumetric flow rate, you multiply with K, katakan kamu dapat 0.1 or less than 0.1, meaning to say even before kamu run kamu punya reaction tu, you already know that your conversion will be less than 10%. Saya tak run pun reaction saya kira je damn column number saya based on the tau K. If I get less than 0.1, I know that my conversion will be very, very low, less than 0.1, less than 10%. However, if I calculate my damn column number 10 or more, katakan saya kira 10 atau lebih, it tells you that very likely your reaction punya conversion is more than 90%. High conversion lah. Okay, so that is something that is very powerful just by knowing damn column number. Saya dah boleh predict conversion in my reactor even before I run my reaction. Okay, so maybe you ask a question, kalau saya tahu conversion saya rendah, apa gunanya? Okay, what do we need to know this? Okay, sama macam Reynolds number. Kenapa nombor ni very powerful? Sebab dia bagi kita indicator, kita dah boleh manipulate certain parameters untuk kita ubah nombor itu untuk ubah phenomenon dia. Okay, contohnya dalam case ni, you know that I need to get my then column number sebesar yang mungkin sebab the bigger it is, the better conversion, right? Okay, so what can I do? Okay, tengok balik. Then column number tu kan kita kira berdasarkan tau K. Okay, first of all kita tengok tau dulu. Okay, so kamu tengok dia berkadar langsung kan? Dan column number tinggi, tau kena tinggi, berkadar langsung. Okay, dalam tau tu, space time tu kan ada volume per inlet volumetric flow rate. Okay, so of course reactor volume kita tak boleh buat apa-apa kan? Reactor volume tu unless kamu nak tukar reactor lah, unless you decided you want to change to a bigger reactor, boleh, possible, one way if you want to change. Instead of using 10 liter, I go to 20 liter, possible. One way, inlet volumetric flow rate, kamu boleh manipulate. So inlet volumetric flow rate tu kamu kena kurangkan sebab kamu kena ingat tau equals to volume per inlet volumetric flow rate. Tau nak besar, inlet volumetric flow rate tu kena kecilkan ataupun kita slow down the volumetric flow rate. Kenapa? When you slow down volumetric flow rate, residence time dia bertambah. Means kalau kita perlahankan flow dia, lagi lamalah molekul tu duduk dalam reaktor sebab kita slowkan dia punya flow rate. One way. So you can adjust, you can manipulate volumetric flow rate. So sebelum ni, let's say kamu set 200 ml per minute, maybe you can change. You use 100 ml per minute, kamu kurangkan. One way. Second way, if you see here K, so kamu tengok dan kalau number nak tinggi, K kena increase. So you remember kita belajar kan, K will increase with temperature according to Arrhenius equation. So means apa saya boleh buat? Saya naikkan suhu tindak balas saya. So maybe before this I use 40 Celsius, I may consider using 60 Celsius. Bila guna 60 Celsius, mestilah nilai K akan meningkat. Kalau nilai K meningkat, then column number pun akan meningkat. Tetapi kamu kena ingat, okay, I told you before, temperature ni tak sangat straightforward sebab kalau you increase temperature, there are possibility ada tidak balas lain yang boleh berlaku. Kan saya kata kadang-kadang dalam reaktor ni, dia impossible satu reaction. Dia mungkin ada lebih banyak reaction, lebih daripada satu reaction taking place. So when you change temperature, you may change the mechanism of the reaction. So kalau kita tukar mechanism, dapatlah produk yang lain. Okay, macam saya kata, the common one is oxidation dengan combustion. Kedua-duanya menggunakan oxygen gas. Just that oxidation occurs at lower temperature, combustion is at slightly higher temperature. So if you increase it too high, the reaction might go combustion dan bukan oxidation, and of course you dapat completely different product. Okay, so although temperature is very powerful, but temperature is also a danger to reaction because it can change different types of reaction. Okay, so you have learned now, come back to this, you have learned why we need to calculate Dam column number and the importance of Dam column number, because it can predict for us the conversion of the reactor even before you run the reaction itself. Okay, done on first order. Okay, now I go to the next one. I change the rate law. So now rate law dia become minus RA equals to KCA square, which is second order with respect to A, and this is still liquid phase. Okay, so still liquid phase, still CSTR. Kita just ubah rate law sahaja, jadi minus RA equals to KCA square. So what happens to the equation? Okay, of course naturally equation pun dah berubah sebab tadi minus RA KCA, sekarang minus RA KCA square. So tadi kalau CA equals to CA naught in bracket 1 minus X, now I have CA naught, I have CA square. So jadi CA naught square in bracket 1 minus X pun kita kena square kan. So when we combine all three, okay, we will get volume CSTR equals to FA naught X per K CA naught square in bracket 1 minus X pun square. So don't forget di sebab dia open book, memang kamu boleh refer kepada equation. But sometimes sudah tertinggal yang kuasa 2 pun tak nampak sangat, tertinggal. Okay, kalau tertinggal salah lah kan. So make sure you check properly. And then this is of course to find volume lah, but depends on the question. Okay, soalan, I give you volume, I give you FA naught, I give you K, I give you CA naught. Maybe you have to find X. So macam itulah, means satu unknown disuruh cari, yang selebihnya information will be given to you. Okay. Then we have the second version as well. So first version if we know FA naught. Second version if we know epsilon naught, volumetric flow rate. So untuk test minggu depan pun macam saya always remind kamu, make sure kamu ambil masa untuk tengok information tu dulu. Don't rush to do the question. Of course nanti, of course our tendency kita nak cepat-cepat solve kan, tapi make sure tengok dulu information tu betul-betul. Sebab contohnya katakan S1U, kalau that information tu volumetric flow rate, inlet volumetric flow rate, kamu tersalah, kamu ingatkan tu adalah molar flow rate. So completely satu soalan tu dah terus salah, daripada the very first part tu dah salah, the entire question tu sebenarnya dah salah. So make sure you don't do this type of mistake. Betul-betul baca, tengok unit tu betul-betul, baru identify apa simbol yang betul. Okay, so the second formula is the version to find if you're given the inlet volumetric flow rate. And lastly, the third version is to find space-time. So sama je. Saya just pindah the epsilon naught, the volumetric flow rate from right to left. So bila saya pindah, yang pengatas akan jadi pembawah on the left hand side. So I get my space time. So on my right hand side akan tinggal X per K CA naught in bracket 1 minus X square. So you can see right, tiga-tiga version equation pun dah berubah completely in comparison to the previous one. Kenapa dia berubah completely? Sebab saya ubah satu je syarat dia, rate law. Dengan hanya menukar rate law pun equation dah bertukar dengan drastically. So that part yang kamu really kena ingat sebab kita ada banyak equation. Okay, now second order pun CSTR liquid, we have Dam column number juga. Tetapi pengiraan dia dah lain sikit. Okay, what do I mean by that? Okay, again, from the space-time that we are given just now, okay, the space-time untuk second order, okay, yang tadi kita buat sebelum tu adalah first order, yang ni second order, space-time dia adalah X per K CA naught in bracket 1 minus X square. So, if you are aware, walaupun konsep space-time tu sama, tetapi cara nak mengira tu dah berlainan apabila kita tukar rate law. Okay, so from this space-time punya formula, for the second order, same concept, saya pindahkan K and CA naught. Basically, saya pindahkan apa-apa yang tak ada X tu, saya pindahkan from right to left. So again, K and CA naught originally kat bahagian kanan, bila pindah ke kiri dia akan jadi pengatas kan. So dia akan menjadi tau CSTR K CA naught. So these three terms is what we call as Dam column number pula. Kalau tadi first order, Dam column number is tau K. Kalau second order, Dam column number tu adalah tau K CA naught. Okay. So sama konsep. If you calculate Dam column number and kamu kira-kira kamu dapat 0.1 or less than 0.1, it says that means even before you run the reaction, you can predict the conversion will be 10% or less than 10%. However, if you calculate 10 dan kalau number kamu more than 10, that 10 or above, then it means that very likely your conversion is higher than 90%, means high conversion lah. Tetapi don't forget, the K dan Corona number ni sekarang ada 3. Ada space time, K, CA0. Okay, so now I have more parameters that I can manipulate. Kalau tadi saya hanya boleh manipulate volume, volumetric flow rate, inlet volumetric flow rate dengan K kan, K melalui temperature kan. One more thing sekarang yang saya boleh manipulate adalah CA0. So kalau second order reaction liquid CSTR, I can also manipulate CA0. Maksudnya kalau saya nak dan Corona number tinggi, I have to increase the concentration of your A initially. So maybe firstly you prepare your A punya concentration 1 molar. So katakan kamu kira-kira bila saya guna 1 molar, then Corona number saya very small. So you know if the then Corona number is very small, conversion very likely pun small. So what I do? I increase the concentration. So one more way, I can increase concentration. Maybe from 1 molar, I use 5 molar. And you kira balik, then Corona number dia tengok naik tak? How much it increase? So you can now you have another additional parameter that you may manipulate, okay, that in order for you to give a better damn Corona number, which give you a better indication that the conversion will be higher even before you run the reaction. Okay, so done on damn Corona number. So if you realize then Corona number ni very powerful, tetapi limitation dia hanya kepada 2 senario sahaja. Either I'm using CSTR liquid first order or CSTR liquid second order. The rest dah tak boleh guna dalam Corona number dah. Dia dah tak boleh diguna aplikasi this prediction tu, dah tak valid untuk any other cases. Okay, so that's all for dalam Corona number. Nanti dalam kamu punya lab 4, experiment lab 4, ada part pengiraan dalam Corona number. Okay, so kalau kamu tak faham, okay, dalam saya punya lab briefing tu, kamu tu tengok slide lab briefing tu sebab I really dah ajar kamu macam nak kira dah pengiraan tu. So hopefully that helps you untuk buat pengiraan. Kamu check je part tu untuk tahu pengiraan dia. Okay, right. So as well as dalam, sebelum saya lupa, dalam lab briefing report tu, lab briefing slide tu, part yang last tu, I also teach you how to write summary, how to write result, how to write discussion, how to write conclusion pun saya dah ada juga masukkan juga. Sebab before this I did a workshop, I think last year I did a workshop for student juga on the lab. So I included that slide as well so that it helps you also to do your lab report. But as I told you, tak payah lab report yang panjang-panjang. That's my mini project pun sama, no need to do panjang-panjang. You fulfill what is needed in the assessment form, I can promise you, you already get the marks. Okay, right, so back to here. Okay, now last one. Kita buat sekarang for CSTR liquid. Rate law dia minus RA equals to KCA/CB. So tadi kita dah buat minus RA KCA. We already do minus RA KCA square. So now we do minus RA equals to KCA/CB. Means reaction tu first order with respect to A, first order with respect to B. So sekarang kita dah involve 2 reactant, A and B reactant. So kes sebelumnya bila kita ada satu reactant, reactant A. Okay. So what's different? The only difference is now rate law lah. Dan juga you can see the concentration. So mungkin kamu sebelum ni tak familiar sangat sebab kita selalu tengok CA, right? Tapi sekarang kita akan tengok CB. So kalau CB you express as CA0 in bracket theta B minus B per AX. So part concentration ni dalam chapter 3 kamu dah belajar, make sure kamu tahu macam nak kira CA, macam nak kira CB. Especially part CB ni because kadang-kadang CB B is a reactant. Okay, kita express concentration dia. Tapi bila B adalah produk, kita express concentration dia a little bit different. So make sure you check macam mana kita nak kira keperkatan B kalau dia adalah produk ataupun bila dia adalah reactant. Okay, right. So come back to here. So same concept. I will again combine 1, 2 and 3. So rate law dia minus RA become KCA/CB. So again I replace CA with CA0 in bracket 1 minus X. I replace CB with CA0 in bracket theta B minus B per AX. Sebab tu kamu perasan we have 2 CA0. So it becomes CA0 square. That's why kat depan tu ada KCA0 square. So If you wonder kenapa jadi CA0 square, sebab CA ada satu CA0, CB pun ada lagi satu CA0. So you know CA0 multiply with CA0, it becomes CA0 square. Sebab tu kita jadi CA0 square. Right. So this is the formula to find the volume when your rate law minus RA equals to K CA CB. Okay, then you know kita ada version kedua. Version pertama kalau kita tahu FA0, kita tahu CA0. Version kedua, if we are given epsilon naught in the inlet volumetric flow rate. So, dia jadi version yang kedua. So, become volume CSTR equals to epsilon naught X divided by K CA naught in bracket 1 minus X in bracket again theta B minus B per AX. So, if you are wondering kenapa yang version kedua tu CA naught, version pertama CA naught square sebab version pertama tu kan kita ada FA0 di atas. So the top FA0 we divide with 1 CA0 at the bottom. Sebab tu kita dapat epsilon naught kat atas. Tapi kita hanya boleh cancel, kita hanya bagi dengan satu CA0. So lagi satu CA0 tu tinggal. That's why at the bottom you have another CA0 yang tak boleh dibatalkan atau tak boleh dibahagikan. Okay. Dan then we have the third version because kita nak kira space time. So kamu kena tengok soalan lah, nak cari space time ke nak cari volume. Kalau cari space time, tengok rate law mana. Okay, then you tengok baik-baik mana satu equation yang boleh digunakan. So for tau CSTR, for this rate law equals to X per K CA0 in bracket 1 minus X in bracket theta B minus B per AX. So theta B you learn in chapter 3, but I repeat again. What is theta B? Theta B is the ratio of initial amount of B over initial amount of A. Ataupun nisbah asal bahan B terhadap nisbah asal bahan A. Okay. Bahan ni, nisbah ni dalam bentuk apa? It depends. Kadang-kadang dalam bentuk mole fraction, kadang-kadang dalam bentuk concentration, molar flow rate, so on and so forth. Bagaimana cara diberi nilai tu tak kisah, yang penting kamu kena bahagi nilai asal B terhadap nilai asal A for you to get theta B. Okay, so mesti akan keluar dalam test bahagian cara theta B ni. Okay, next, B per A ni. So B per A ni you have to be very careful. You have to see the stoichiometric coefficient. So bila tengok soalan reaction tu, tengok betul-betul tindak balas dia, tahu stoichiometric coefficient dia, ganti dengan betul-betul. So I always tell my students, sebenarnya reaction dia kalau actually it's easy. Bukan nak cakap senang. Tapi kalau kalau you faham, if you really understand or you get the concept, reaction is very very easy if you get the concept. Tetapi I can understand, kalau tak dapat konsep tu memang dia sangat mencabar. So it's always the case when if the student get the concept, they can score very well. Kalau tak dapat konsep tu, tapi sebenarnya you trust me, it's just about understanding the concept. You don't have to be smart, you don't have to be super genius to do reaction. You can ask your seniors. Most of the time it's just dia kalau dah dapat kan, benda tu senang je semua. Dia kalau tak dapat tu yang susah sikit sebenarnya. So make sure you really check, you really understand. Reaction is very very doable. You can really ask your seniors, it's very very doable actually. Right? Okay. Come back to this. Right, so I've done ready for CSTR liquid phase. So sekarang kita susahkan sikit hidup kita terpaksa buat untuk gas phase. Okay, so of course some student might ask, tapi kan bukan doktor pernah kata ke gas phase ni kita guna PFR, kita jarang guna CSTR. It is true indeed that we rarely use gas phase untuk CSTR, tetapi tak bermaksud tak guna. Ada je sebenarnya case where we use gas phase untuk reaction in a CSTR. Although rarely, but it does happen. So we have to address that as well. Katakan kalau ada case, you use gas in a CSTR. Okay. So next question come up. So apa beza dia kalau kita guna gas? Kenapa kita kena belajar balik equation ni semua? Sebab satu je benda, sebab concentration kita dah berubah. So nanti kamu tengok balik chapter 3 kan, sebab test ada bahagian chapter 3 kan. So chapter 3 kamu dah belajar. Kita express concentration kalau PFR, CSTR. Concentration gas, concentration liquid tu berbeza sama sekali. So nanti dalam soalan test kamu check betul-betul. Saya suruh cari concentration gas ke? So saya suruh kamu cari concentration liquid. So kamu kena betul-betul check. So beza dia, if you remember, kalau concentration liquid, Ca equals to Ca0 in bracket 1 minus X. Tetapi kalau dia dah gas, dia tambah pembawa dia dalam bracket 1 plus epsilon x. Itu perbezaan dia. Dah ada pembawa dia. Okay, tapi kamu jangan lupa, barat ada gipat kan, yang pressure dengan temperature kan. Tapi setakat kita belajar ni, we just learn no pressure drop, no temperature change. That's why the P0 per P, T per T0 tu tak ada. But later, shortly later, about 10 minutes later, I will teach you kalau kita include pressure change, apa yang berubah, apa yang berlaku. Okay, so itu yang berbeza sekarang. CB pun sama. So previously CB is equal to CA0 in bracket theta B minus B per AX. Sekarang kalau gas, tambah yang pembawah 1 plus epsilon X. So epsilon pun kamu kena belajar macam mana nak cari epsilon. Make sure you really know. So epsilon tu apa? Epsilon tu sama dengan YA0 sigma. Sigma tu apa? Sigma tu ratio of stoichiometric coefficient. So benda ni semua kamu kena tahu. So kadang-kadang kalau nak jawab soalan kan, macam reaction, kalau kamu betul-betul tak tahu macam mana nak buat, let's say you don't know the how to solve it, you try to find all this. Macam kamu try lah cari CA0 ke, cari FA0 ke, cari epsilon ke, cari theta B ke. So at least you got marks for finding this. So don't leave it blank. You just do certain calculation. Katakan kamu tak tahu macam nak kira keseluruhan, tapi kamu tahu mesti kena ada theta B. So kamu kira lah theta B. Ataupun kamu tahu mesti ada epsilon. Kamu tak tahu macam nak solve, tapi you know must got epsilon. So you solve epsilon tu berapa, so on and so forth. Okay, right, so done. So then again, we have to do all over again the equation. Okay, so kita buat balik untuk first order, but now this is gas phase. Gas phase, first order, CSTR. Okay, so you tengok beza dia sebab concentration tu dah menjadi Ca equals to Ca0 in bracket 1 minus X per 1 plus epsilon X. Okay, so when we combine, okay, you can see derivation ni a little bit of mathematics sebab sekarang dia ada 3 layer kan, sebab at first Fa0x per minus Ra. Minus Ra dia adalah KCa. Okay, then di express Ca tu kan dah sama dengan Ca0 in bracket 1 minus X per bracket 1 plus epsilon X. So kamu tengok kita ada 3 layer. So whenever you do mathematics, you just remember yang third layer tu, the bottom layer goes to the top. So 1 plus epsilon X ni naik ke atas, multiply with tadi yang Fa0x, yang kat bawah tinggallah KCa0 in bracket 1 minus X. So ni adalah sama dengan volume CSTR. So sama je konsep. Okay, version pertama, kalau kita tahu Fa0, kita tahu Ca0. Kita boleh guna version pertama. So make sure kamu tahulah macam nak kira Fa0, nak kira Ca0, nak kira epsilon. Betul, you can find an X untuk cari volume. Then the green one is for if let's say you know the epsilon naught, the inlet volumetric flow rate, I can use the second version. So macam mana second version tu wujud? Sebab I just divide one Fa0 at the top with one Ca0 at the bottom. If I divide, I get the epsilon naught. Okay, yang lain masih sama. Then the third version is to find space-time. So sama je konsep. Nak cari space-time, saya pindahkan sahaja epsilon naught from right to left. Dia jadi pembawa. I get the space-time on my right, on my left. On my right will be the yang selebihnya lah. Macam ni, X in bracket 1 plus epsilon X per K 1 minus X. Okay, right. Next one is for second order. So second order reaction pun sama, tapi kamu tengok dia jadi lebih kompleks kan sebab dah second order. So tadi Ca0, Ca equals to Ca0 in bracket 1 minus X per 1 plus epsilon X. Tapi sekarang kan dah menjadi KCa square, second order with respect to A. So Ca square akan jadi Ca0 square in bracket 1 minus X square. In bracket lagi 1 plus epsilon X square. So nanti kita buat tutorial naik sem break, nanti kita buat tutorial, kamu akan tengok pengiraan ni kompleks lah sebab ada quadratic, you have to solve the quadratic, so on and so forth. So another new thing that is complexity dia sebab dalam equation ni kita ada quadratic sebab dia adalah 1 minus X power of 2. Okay, so same concept, I got version 1, version 2, version 3. So version 1 is if I know Fa0, I know Ca0. Version 2, if I know epsilon naught, the inlet volumetric flow rate. The version 3 is to find space-time. So dia yang version tu sama je konsep dia, tetapi equation dia berlainan sebab as I told you, you tukar rate law ke, you tukar gas, you tukar phase ke, dan that's why dia dah jadi berlainan. Okay, and the last one for CSTR, okay, is when we have the rate law minus RA equals to KCA-CB. So you check question. Kalau soalan tu kata the reaction is first order with respect to A, first order with respect to B, has rate law dia minus RA equals to KCA-CB. So kami ingatkan dalam chapter 3 kita recap balik macam mana kita nak tahu rate law dia. Kamu akan tengok soalan tu kata tak elementary rate law ke non-elementary rate law. So kalau dia kata reaction obeys elementary rate law, reaction order tu kamu ikut je stoichiometric coefficient. Kamu ikut nombor dalam persamaan kimia. So contohnya katakan reaction tu 1A produce 1B. 1A menghasilkan 1B. Lepas tu dia kata the reaction follows stoichiometric coefficient. The reaction obeys elementary rate law. So kamu tahu, okay, satu reaktor saja kan? So minus RA equals to KCA power of 1 sebab nombor di hadapan A adalah 1. So kamu tulis ikut je nombor dia. Katakan if the equation reaction is 1A with 1B to produce 2C. So dia kata it follows elementary rate law. So minus RA equals to K, CA power of 1, CB power of 1. Ikut je stoichiometric coefficient. Tetapi if dia kata, soalan tu kata reaction ni non-elementary rate law ataupun dia tak kata pun tapi dia terus bagi rate law dia. Contohnya katakan reaction dia 1A produce 1B. However, the question kata the reaction is second order with respect to A. Kamu kena ikut information yang diberi, kamu dah jangan tengok persamaan kimia. Kamu hanya tengok persamaan kimia kalau dia kata elementary. Kalau dia tak kata elementary, kamu ikut information yang diberi untuk kamu tulis rate law dia. Okay, so back again. So same concept lah, kita dah tahu CA, kita dah tahu CB, we express in the form of for the concentration of gas phase. Okay, so just that part ni kita tambah CB lah. So CB become CA0 in bracket theta B minus B per AX over 1 plus epsilon X. So again, we combine. Okay, so we get the first version, second version, third version. So you can see untuk CSTR ni memang tak payah terang banyak sangat sebab you will understand it's basically I express CA in the big form, in the long form. CB also I have to combine. I have to express in the longer form, and then I combine yang kat bawah layer ketiga naik ke layer atas, so on and so forth. Eventually you get the three version, okay, of the equation, of which the last version is to find space time. Okay, so you realize sebenarnya you already learn 3, 6, 9 times tu 18 equations sebenarnya, di mana yang paling penting untuk kamu faham bukan untuk menghafal. Yang paling penting untuk kamu faham kenapa kita ada 18 equation first. Second, data the unknowns tu kamu tahu apa maksud dia. Apa tu FA0, apa tu CA0, what is X, what is theta B, what is epsilon. Tu yang penting. Application equation tu is more important than memorizing the equation. That's why I said kalau macam test satu, final exam pun macam tu is really open book. You can refer to any notes you want to Google pun boleh. Just that you cannot copy from your friend. Itu satu benda kamu tak boleh buat. Kamu tak boleh discuss dan copy from your friend. Okay, right. Next one, okay. So I done on deriving the equation. Okay, so kamu dah belajar setakat ni, if I remember correctly, about dah 30 equation. Okay, tapi tak habis lagi. Kenapa? Sebab all this while I told you, kita hanya learn until untuk case di mana there's no pressure change. Okay, maknanya kita assume semua tindak balas, kita design, kita cari equation 30 equation tu. 30 equation ni hanya untuk tindak balas di mana there's no pressure change. However, often there are cases where akan ada pressure change or more exact, pressure drop. Okay, so what happens when we have pressure drop? Okay, the good news is that although pressure drop will have effects on our reactor design, however, untuk case liquid phase, this effect can be ignored. Maknanya untuk case liquid phase punya equation design, ataupun if let's say your reactant is liquid phase, perubahan tekanan tu takkan mempengaruhi pengiraan kita. So before this you learn dah banyak equation kan. Equation yang part liquid phase tu kamu dah tak payah bimbang. Dia takkan dikacau. Ada pressure change, tak ada pressure change pun equation tu tetap sama. Tetapi the unfortunate part, untuk gas, this is no longer applicable because remember I taught you in chapter 3. So yang ni kamu dah kena tahu outlet untuk gas phase, kalau liquid outlet sama dengan inlet volumetric flow rate. Sebab tu formula kita tak berubah langsung, sebab inlet outlet volumetric flow rate for liquid, regardless gas ke regardless perubahan tekanan ke, dia masih sama. Tapi for the case of gas phase dah tak, sebab outlet volumetric flow rate sama dengan inlet volumetric flow rate in bracket 1 plus epsilon x yang kita belajar selama ni. Dan sekarang kalau ada you have pressure drop or pressure change, means katakan ada kenaikan pressure ataupun penurunan pressure, you already have to include the P naught per P. P naught per P ada dalam equation. So part ni lah actually yang menyebabkan all diesel equation yang berkaitan dengan gas akan berubah, sebab kita kena include part P naught per P. So sebelum ni kamu belajar kan yang gas phase kan kita belajar banyak equation kan, PFR dengan CSCR saja batch tak apa. So before I forget, kalau batch liquid ke gas sama je, tak ada berubah. Okay. Kalau flow liquid sama, hanya gas yang berubah because now kita kena include P naught per P. Apa tu P naught per P? P naught is initial pressure, P is the outlet pressure ataupun pressure selepas tindak balas dah berlaku. P naught sebelum dia berlaku. So, what happened to the equation? Okay, yang tadi kita dah derive kan banyak-banyak dan kita derive daripada minggu lepas kepada minggu ni. Kalau kamu tengok, beza dia adalah yang part merah ni. Kita kena tambahkan yang part merah ni dalam design equation kita. So, yang sebelum ni saya ajar, kamu dah pernah belajar derive ni. Just that, kalau ada pressure change, either pressure drop or pressure increase, you see now we will include the P naught per P in the final equation. Okay, so again, make sure you check betul-betul. Maknanya equation akan berubah untuk PFR, CSTR, gas phase. Yang saya ajar sebelum ni tak ada part yang merah tu, P naught per P tu tak ada. Tapi sekarang dah ada. Okay, so bila kamu tengok soalan test 1 tak payah bimbang, test 1 tak ada part ni. Test 2, final exam, kamu kena betul-betul refer, tengok ada pressure drop ke tak ada. Kalau ada pressure drop, kamu kena refer kepada note bahagian ni. Kalau tak ada pressure drop, refer to the previous part. Okay, this is for PFR. This is for CSTR. Jadi tadi kita belajar kan, saya kata saya ajar kamu berapa banyak equation, 9 equation tu untuk gas. So sebelum ni kalau masa saya ajar kamu, kamu perasan tak ada P naught per P kan? Tapi sekarang dah masuk part P naught per P sebab kita dah ada pressure drop. Okay, so nanti later in chapter 6, kita introduce pula when there's a change of temperature. Sebab tu if you perasan reaction ni, you have to understand konsep pertama, then naikkan susahkan sikit konsep kedua, then bila naik ke chapter 6 susah sikit, kita dah tambah when there's a change of temperature. Okay, so I didn't teach you lah how to derive again, tak lah, tapi just that remember kalau ada pressure drop, design equation yang kita belajar sebelum ni, kita kena tambah part P naught per P in your equation, right? So done on pressure drop. Okay, so we left the last part for today. So today you will finish your class much earlier than usual. Okay, just to give you more time to do your mini project, to do your test. So we go to the very last part. So to the very last part is sekarang tambah lagi satu kesusahan. Okay, before this we learn irreversible. Kan ingat kita belajar irreversible reaction, contohnya tindak balas yang tak berbalik kan, first order reaction, second order reaction. So minus RA equals to KCA, or second order reaction minus RA equals to KCA square ataupun minus RA equals to KCACB. all these are irreversible reaction, of which maksudnya the reaction goes forward direction. However, you need to understand there are reaction yang mana dia boleh berlaku both direction. Meaning, let's say in this example, you see I got two reactant, two product. Okay. If it's irreversible, my A and my B will always move forward, will react forward to produce C and D. However, in reversible reaction, there is additional backward reaction, of which my C and D can also react to form back A and B. So it goes forward, backward, Okay, tetapi kamu kena ingat, untuk tidak reversible ni, kamu imagine kamu ada reversible, during the reaction, okay, let's say you start the reaction, semasa the reaction takes place, dia akan pergi forward, backward. Maksudnya, kadang-kadang kepekatan C dan D akan naik. Kadang-kadang kepekatan A and B akan naik. Sebab kalau dia forward, C and D naiklah, lagi banyak C and D terhasil. Tapi masa yang sama, C and D pun boleh bertindak balas menghasilkan A and B kan. So masa kamu catat, katakan kamu rekod kepekatan all of these 4 compounds, minit pertama mungkin kamu tengok C and D tinggi, A and B rendah. Minit kedua maybe A and B naik balik, C and D rendah. So on and so forth. So it goes forward, backward. So kepekatan dia berubah-ubah. However, eventually it will reach what we call as equilibrium, keseimbangan. Selagi kamu tak kacau sistem tu, kamu biar je tindak balas berlaku, it will reach equilibrium. Okay, apa maksud dia equilibrium? Means pada equilibrium, the concentration of all these compound are the same and dia dah tak berubah. Dia takkan naik, takkan turun, dia dah maintain equilibrium lah, maintain seimbang sudah. So when they maintain the same concentration, kita akan cakap dia dah mencapai keseimbangan. Unless kamu kacau sistem tu. If you disturb the system, then tak adalah. But if you don't disturb the system, eventually dia akan mencapai keseimbangan. The concentration of product, concentration A, B, C dan D remain the same. Okay, at this equilibrium, okay, katakan kamu cari dia punya kepekatan. Kan I told you the concentration is remain the same. Dia dah tak berubah. Okay. Kepekatan dia of course tak samalah. Dia saya kata kepekatan dia tak berubah means dia dah stay constant. Katakan A tu 1 molar, B tu 2 molar, C tu 2 molar, D tu let's say 2 molar. 1 tu 2 ni kekal maintain. Kamu kacau macam mana pun masih kalau kamu tak kacau sistem dia, kamu biarkan 10 minit ke berapa minit pun bila dia dah capai keseimbangan, it's still 1, 2, 2, 2. Okay. At this moment, when you calculate the concentration, is actually correlated to what we call as equilibrium constant, Kc. So sekarang, you learn another new unknown, kita call Kc. Sebelum ni you learn K, right? K, reaction rate constant, pemalar kadar tindak balas. Today you learn Kc, equilibrium constant. Okay, what is equilibrium constant? Equilibrium constant tu adalah bila kamu kira the concentration of your product over concentration of your reactant. That value is what we call as Kc. Ataupun we can also say Kc as the ratio of reaction rate constant forward over reaction rate constant backwards. You will get your Kc. Or you calculate in terms of concentration, di mana pengatas dia adalah concentration product. Sebab forward kan, forward dapat product kan, so concentration product di atas, bawah dia concentration reactant sebab backward reaction. Then kamu ingat, Kc is only calculated at equilibrium. Kamu tak boleh kira Kc sebelum equilibrium. Selagi equilibrium tak capai, you cannot calculate Kc. Kenapa? Sebab kepekatan tu akan sentiasa berubah-ubah. Kamu kira Kc minit pertama takkan sama dengan Kc minit kedua kalau dia tak capai keseimbangan. Sebab katakan dia dah reach keseimbangan at minute 10, you calculate the Kc minit 10, minit 11, minit 12, minit 13, sama je nilai dia. Sebab the concentration no longer changes, no longer increase, no longer decrease. Okay, so that's why you realize kita letak sebagai CCe power of C. What is that? So C concentration, right? The subscript C, compound C. ada subscript E. Subscript itu to signify the concentration of C at equilibrium. Power of C itu apa? Power of C itu adalah dia punya stoichiometric coefficient. So dia adalah Kc sama dengan kepekatan C at equilibrium, power stoichiometric coefficient C dalam the chemical equation, multiply with concentration of D at equilibrium, power D stoichiometric coefficient. So why C and D ke atas? Sebab in this reaction C and D is the product. So equilibrium constant tu mesti kira yang forward bahagi dengan yang backward. So yang backward tu jadi concentration of A, concentration of B at equilibrium, power stoichiometric coefficient dia A and B. So when you do this, you will get actually your Kc. Yang penting kamu kena faham is evaluated at equilibrium dan juga pada bila kamu mencapai keseimbangan, conversion tu pun kita panggil sebagai equilibrium conversion. Okay, so tak apa kalau kamu confuse part equilibrium conversion, dia macam ni. Okay, alright. So saya akan ajar kamu sikit lagi. Right, now. Sama konsep macam concentration, kamu perlu bacakan Ca, Cb, Cc, Cd. Masalah dia adalah kita tak ukur Ca, Cb, Cc, Cd. We will always measure in terms of X and Ca0. So sama je. For my concentration of A at equilibrium, okay, I must also express in terms of Ca0 dan X. But I can no longer write as X sebab the X is very specific at equilibrium. Sebab tu dia menjadi CAE, concentration of A at equilibrium, equals to concentration, initial concentration of A, Ca0, in bracket 1 minus XE. Saya kena tulis X tu, saya kena tulis sebagai XE sebab that is to signify the conversion at equilibrium. Conversion sebelum dia mencapai keseimbangan, kita panggil conversion biasa. Conversion pada keseimbangan is what we call as XE. And if you remember I taught you, bila dia dah mencapai keseimbangan, itu adalah the highest conversion possible for that reaction. Katakan conversion equilibrium dia, equilibrium conversion dia adalah 88%, 0.88. X kamu 0.88. If you don't disturb the system, okay, macam mana kamu buat pun, itulah the highest conversion that they can achieve. Because the reaction dah capai keseimbangan, kepekatan dah tak berubah, dia maintain sama. So that's the highest conversion possible. Okay, so katakan saya nak tulis, want to express Kc untuk case batch dan liquid flow. So kita nak express balik, kita nak cari balik kan CAE, CBE, CCE, CDE. Kamu kena ingat sama konsep. Kalau dia adalah gas flow, expression dia dah berlainan. Untuk batch dengan liquid flow, expression dia is the same ataupun basically dia tak ada pembawa. Kalau batch dengan liquid flow, dia tak ada pembawa yang 1 plus epsilon X. Kalau dia adalah gas flow, tambah yang part 1 plus epsilon X yang pembawa tu, dan tu kalau ada pressure, letak juga part yang ada pressure yang P0 per P. So that is how we express Kc. And then the next one adalah for you to avoid confusion. Okay. Yang tadi contoh yang saya discuss is when you have two reactant A and B. Tapi remember sometimes there are certain reaction we use one reactant. So if we use one reactant, produk dia, produk pertama tu dah menjadi B kan. So bila produk tu menjadi B, kamu kena ingat kita dah express the concentration dah lain sikit. So bila dia adalah produk, CB at equilibrium equals to B per A, Ca0 Xe. Okay, kalau dia adalah reactant, CBE equals to Ca0 in bracket theta B minus B per A Xe. So because one is reactant, one is product, concentration dia express lain, kita nak cari Kc pun dah lain. Okay, tapi tak apa kalau part ni you get confused. We will discuss one question before we end for today and then you probably will understand it better. Kenapalah kita kena tahu benda ni. So sometimes memang reaction kalau tak tengok contoh memang it looks very complicated right, in terms of symbol, but later when you see question it's slightly easier for you to understand. Ada arti kata lain, apa yang kita buat dalam slide ni, if you want to find Kc, kita nak cari, kalau kita tahu Ca0, kita tahu Xe, kita nak cari Kc. Itu sebenarnya in the simpler way for me to tell. Okay, so done. on Kc. Okay, so this one pula is for you to find for the case when gas phase flow reactor. So kalau gas phase flow reactor, kamu nak cari Kc. Okay, beza dia adalah just I told you sebab concentration dah express berlainan. Sebab tu equation dia pun dah express berlainan. Okay, so kalau kamu perasan, mungkin if you have your senior note, kamu tengok ada setempat tu saya tambah lebih lagi semester ni. Kenapa saya tambah? Bukan saya nak bebankan kamu, tapi I rest that macam saya cakap kalau I assume student tu tahu, student tu boleh kaitkan balik chapter 3, sebabnya ni kamu belajar chapter 3 kan, ni apa tu, I assume that the student can correlate to chapter 4. But then I realise sebenarnya tak semudah itu sebab yalah, if you only learn reaction your entire life, boleh lah kan macam I only teach reaction, I teach design project, plan design. So of course it's easier for me to able to correlate. But for you, I can understand you got a lot of courses, you got a lot of formula. It's impossible to correlate ataupun betul-betul tengok correlation dia. Sebab tu dalam notes for this semester, I dah letak terus correlation dia. Means kamu dah tak payah assume, kamu dah tak payah agak, saya dah letak terus. Tapi dia punya downside dia bila saya letak, it can be a bit confusing sebab kamu tengok ni mesti kamu terasa banyaknya equation, tetapi tak apa, nanti kita buat soalan, you can understand it better. Reaction kalau tengok formula memang susah nak faham, tapi kalau ada soalan is easier to understand. Okay, so later I will explain in the terms of answer. You can see easier macam mana kita nak kira Kc ni kalau kita ada gas, kalau kita ada liquid. Right, so done. Next one. Okay, so this is maybe one simple example. Kita try one simple example nak cari Kc. Okay, so katakan we have this reaction. 2A react to produce 1B and 2C. So again, if you don't know how to check the reaction is reversible or irreversible, kalau reversible kamu tengok anak panah tu ada dua belah, two direction. So that signify reversible, or in test or exam, I will write clearly lah the reversible reaction so that you really would not be confused. Ni reversible ke irreversible? Okay, katakan kita nak cari Kc for this reaction. Kita nak cari pemala keseimbangan, equilibrium constant. So Kc equals to ada top, ada bottom. Top dia adalah concentration of your product at equilibrium power stoichiometric coefficient. Means in this case I got two product, right? B and C. That's why it becomes Cb at equilibrium, Cc at equilibrium, then power stoichiometric dia. For B, the stoichiometric coefficient is 1. That's why Cbe power of 1. Stoichiometric coefficient for C is 2. So Cce power of 2 divided by concentration of your reactant at equilibrium power stoichiometric coefficient. So it becomes CaE power 2 because in the chemical equation, the stoichiometric coefficient for A is 2. So power of 2. Okay, lepas tu kita kena express dalam bentuk concentration sebab satu U kita selalu dalam kira concentration dalam bentuk Ca0 dan X. Kalau equilibrium, Ca0 dan Xe. So kamu kena tengok balik chapter 3. Kalau B adalah product, if B is a product, the concentration Cbe now equals to B per A Ca0 Xe. Sebelum ni kamu belajar sebagai B per A Ca0 X. Just that X tu jadi Xe sebab sekarang pada equilibrium. So same for C. Concentration dia expressed as C per A, Ca0 X. Just that not at equilibrium jadi Xe. Then since dia kuasa 2, the concentration of C pun kena kuasa 2, divide by Cae power of 2. Before this you learn Ca equals to Ca0 in bracket 1 minus X. So sekarang kalau Cae power of 2, so become Ca0 in bracket 1 minus Xe, tutup bracket power 2. So beza dia, express tu sama, just that dia punya equilibrium conversion, conversion tu jadi equilibrium conversion. Okay, you may ask, kenapa Ca0 ni tak ada E? Sebab CA0 ni kan initial concentration, regardless sebelum kesimbangan ke, selepas kesimbangan ke, concentration asal yang kamu prepare tu masih concentration asal yang sama. The concentration, initial concentration will not change. Initial kat equilibrium ke, sebelum equilibrium ke, yang kamu prepare masih perkataan is still the same concentration. Okay, so next, just pembatalan sajalah. Kita ganti stoichiometric coefficient, so on and so forth. And then finally, we get the final derivation. So, since this question, they didn't tell us equilibrium conversion tu berapa, so we cannot solve. But let's say you're given equilibrium conversion as, let's say, 0.4. So, you replace lah. Then you will get the Kc value in terms of numbers. So, ni sana tak ada nombor sebab kita tak tahu Xe. Right, next one, a little bit more. Okay, now we learn Kc. Next, we learn rate law. So, again, kamu kena faham, you have to understand. Reversible reaction, rate law dia pun sama konsep macam irreversible. Whether is elementary rate law or non-elementary rate law. So again, I repeat, for reversible reaction, similar to irreversible, you have either the reaction follows elementary rate law or it doesn't follows elementary rate law. Okay, apa beza dia? Kalau if it is non-elementary rate law, maknanya the information has to be given to you. Sama je konsep dia. Katakan kamu ada reversible, soalan kata it follows non-elementary rate law. So the question will further give you information. The reaction is first order with respect to A, blah blah blah. So kamu ikut je information diberi. However, if they says the reaction follows elementary rate law, this sekarang dah ada special formula that you have to follow. Dia punya rate law. Okay, so rate law dia untuk elementary reversible reaction. Again, I repeat, if it's reversible elementary rate law dia is written as minus RA, masih sama, equals to K, masih sama, reaction rate constant kan, kita ingat kan? Sekarang dalam bracket tu yang dah lain sikit. Apa lain dia? Okay. Sebelum ni, kalau dia adalah irreversible, kita just tengok concentration of reactant kan. Alpha tu reaction order. Okay. Kita tengok kan. Kita tengok only concentration of your reactant. Ca, alpha. Alpha ni apa? Alpha reaction order kan ikut stoichiometric coefficient. Macam case irreversible. Alpha tu kita tengok stoichiometric coefficient. So part tu masih sama kan. So kalau dia adalah irreversible, kita stop kat sini. Tapi sekarang ni adalah reversible. So that's why ditambah yang part belakang. It become minus CB power of B per KC. Okay, so don't forget, tindak balas ni adalah 1A, 1B. So the front part is for the reactant, the back part is for your product. So this reaction I have one reactant A, one product B. That's why it becomes Ca power alpha. Alpha, you see the stoichiometric coefficient minus Cb power beta, you see stoichiometric coefficient per Kc. Kc tu apa? Kc adalah equilibrium constant yang tadi kamu belajar tu. So kamu tengok rate law dia dah completely dah berbeza kalau dia adalah reversible elementary rate law. Kalau nak elementary, kena tengok soalan, information diberi. Kalau elementary, kamu kena betul-betul ingat cara derivation ini. Okay, then next case. Now, katakan I have two reactant, two product. A and B is my reactant, C and D is my product. Okay, so it become minus RA equals to K. Okay, in bracket, concentration of my reactant, Ca, Cb, power alpha beta follow your stoichiometric coefficient, minus concentration of product C and D. So Cc, Cd, power stoichiometric coefficient C and D divided by Kc, equilibrium constant. So again, rate law dia pun kamu kena betul-betul berhati-hati because the previous example B was a product. Kalau B product, concentration B muncul kat belakang kan. Tapi kalau B in this example is now the reactant. So, so the concentration of B sekarang muncul kat depan. Okay, some of you may ask, kenapa A, B, C, D tu tak ada equilibrium? Okay, sebab for this rate law, kita bukan sahaja measured pada equilibrium. We are talking about rate law of which we measured during the reaction before the equilibrium is achieved. Okay, and actually kalau kamu kira minus RA pada equilibrium, kamu akan dapat sebenarnya nilai dia adalah kosong pada equilibrium. Kenapa? Sebab if you realize, atau you equilibrium kan, kepekatan dia tak berubah kan? When you kira at equilibrium, minus RA itu kosong. Sebab tu kita takkan kira minus RA pada equilibrium. We will calculate minus RA before the equilibrium is achieved. Sebab tu bila kita nak pilih conversion ataupun kita nak set conversion reactor, we will not choose ataupun we will not go to the equilibrium conversion. We will always choose the conversion or we target conversion bawah equilibrium conversion. Okay, so done, right? So before we finish, okay, one example, then we are done for today. So we are done by 6:15, 6:20, we are done for today. Okay, so the question says, the gas phase isomerization reaction given as following. So 2A isomerize jadi 1B. Okay, so dia kata reversible reaction carry out in an isothermal constant pressure flow system with pure A at initial concentration of 0.07 mole per liter and flow rate of 30 liter per second. Given reaction rate constant 110, equilibrium constant 0.8. So let me recap back what information that we know. So first of all, this is gas phase. Walaupun dia kata flow system, tapi kamu ingat gas phase flow system. So by now kamu kena faham gas phase flow system tu kamu dah tahu. Dia punya concentration tu we have to express it different already. First, second dia kata pure A. So initially 100% A, maksudnya mole fraction A is 1 initially, YA0 is 1. So kenapa YA0 1? Sebab initial mole fraction of A is 100% A, so YA0 1. Tu dia kata initial concentration 0.07, so CA0 0.07. Flow rate 30 liter per second. So by right now you know lah kan, liter per second, volume per time. This is volumetric flow rate and this is the initial volumetric flow rate, epsilon naught, 30 liter per second. Given reaction rate constant 110, K 110, equilibrium constant 0.8, Kc 0.8. So nanti bila test minggu depan pun macam ni, kamu dapat setiap ayat tu kamu try convert dulu menjadi simbol. So maksudnya okay, CA0 0.07, epsilon naught 30 liter per second, K 110, Kc 0.8. So you write down first the information in a systematic way. So next dia kata determine equilibrium conversion. This so kita cari XE. Dia nak kita tahu berapa equilibrium conversion itu ataupun berapa banyak conversion of A itu pada masa dia mencapai keseimbangan. First, second part, calculate the CSTR volume if given reactant A conversion is 85% of the equilibrium conversion. So dalam part kedua dia suruh kita cari volume reactor. Tapi dia kata volume reactor tu conversion dalam reactor tu adalah 85% of the equilibrium conversion. So as I told you before, baru tadi saya beritahu kamu, kita jarang target conversion dalam reactor kita adalah equilibrium conversion. We will always target a conversion lower than equilibrium conversion. Logik lah, sebab kalau equilibrium conversion, kamu kena ingat equilibrium conversion tu kedua tu dah seimbang. Tapi kita punya target, kita masih nak produk. So in order to get the product, we will run our targeted conversion below the equilibrium conversion. And in this case, this is 85% of your equilibrium conversion. Maksudnya katakan equilibrium conversion kamu dalam part A kan kita cek equilibrium conversion. So let's say the XE is 80%. XE tu 0.4. Katakan dia kata 85% of the equilibrium conversion, maksudnya conversion dalam reaktor kita, X kita adalah 85% of your 0.4 of your XE. So XE tu 0.4, X saya adalah 85% of my XE. So katakan XE tu 0.4. So saya akan darab 85% of my 0.4, I will get my reactor conversion. Okay, tapi tak apa, kita tengok dulu macam mana kita nak selesaikan this problem. Okay, so first of all, we want to find KC. Tak apa, kamu tak panjang-panjang kan? Okay, we do slowly first. So first part, you derive first. How to find KC? So kamu tengok line yang paling bawah, KC sama dengan, as I told you, concentration of your product, power stoichiometric coefficient divided by concentration of your reactant, power coefficient at equilibrium. So it becomes CBE, the direction is 2A and 1B, right? So CBE per CAE power of 2 because 2A produce 1B. Okay, then if you remember, kita kena express lah concentration kita kan. So CAE, this is gas phase flow system. So CAE equals to CA0 in bracket 1 minus XE per 1 plus epsilon XE. Before I forget, saya dah terjam satu step. Kenapa kita kena cari KC ni? Sebenarnya sebab dia nak cari XE, dia cari equilibrium conversion. So if you realize, the only information yang cakap pasal equilibrium adalah equilibrium constant. So kita tahu equilibrium constant is related to the equilibrium conversion sebab kita tahu KC. If I know KC, I can find my equilibrium conversion. Sebab tu saya guna equation yang KC itu. Okay, so come back to this. So from this concentration that I derive, kita nak cari XE kan? Kalau kita cari XE, meaning the rest tu, the number kita dah kena ganti dengan nilai. Contohnya CA0 given in the question 0.07. CA0 is 0.07 from the question. Okay, XE kita nak cari. So XE we stay. Okay, bawah dia ada epsilon. Okay, so epsilon, kamu kena ingat macam mana kita nak cari. So let us do together sebab dalam test kita dah will come out on how to find epsilon. So better we practice one time. So epsilon is equal to YA0 sigma. Okay, if you forget, memang formula dia YA0 sigma. YA0 tu apa? YA0 tu adalah fraction A initially. So dalam soalan dia kata pure A. So kalau pure A, initially 100% A. So YA0 tu 1. Dalam bentuk pecahan dia menjadi 1. Okay. Sigma. Okay, sigma ni formula dia tak ada fix sebab it depends on the chemical reaction. In this chemical reaction, B is a product, A is reactant. So dia ada jadi positive for product, negative for reactant. Dia adalah ratio stoichiometric coefficient dia. That's why jadi positif B per A. Technically positif tapi tak letak tambah pun kita faham dah dia adalah positif. Positif B per A minus technically A per A. Kenapa minus? Sebab reactant kena minus. Minus A per A. So A per A itu apa? A per A itu 1 lah. That's why we put it as minus 1. So B per A is 1/2. So kamu tengok betul-betul nombor dia. 1/2 minus 1 multiply with YA0 1. You get your epsilon to negative 0.5. So it is possible to get epsilon of a negative value. Okay, so you replace your epsilon kat bawah as 1 minus 0.5 XE. Then you do for CB pula, CB at equilibrium. So CB at equilibrium equals to B per A, CA0 XE per 1 plus epsilon XE. So B per A from the equation, B per A is half or 0.5, actually it's 1/2. 1/2, 0.5 lah. CA0 kita replace dengan 0.07. XE kita nak cari, bottom epsilon tu sama je, minus 0.5. So what you do is, you have to combine kesemuanya. Kalau kamu perasan, KC kita tahu equilibrium constant 0.8. Right hand side, kamu dah ganti kesemuanya dengan nilai besides XE. So you can solve this, you will be able to obtain XE. However, nanti kamu try to practice sebab ni pun tak straightforward equation sebab ada quadratic. Tetapi surprisingly last week I asked you to calculate kan the long equation. Some of you did answer. Thank you so much, and actually all of you got the right answer. So I find that is very good. So means okay, at least you understand the mathematical operation, you understand the equation, you can actually calculate. So for those who answered last week, thank you so much, and actually your answers, all of you answers are actually correct. The difference in the significant figures, you don't have to worry, okay, sebab nanti bila kamu jawab pun, all of the time saya akan tekan balik kalkulator saya juga. So kalau tekan kamu dapat jawapan kamu dan jawapan kamu berbeza sikit sebab of the significant figures, you will not be punished. Saya terima je jawapan tu sebab saya pun akan tekan kalkulator kira balik sebab sometimes dia kan ada banyak step kan. So maybe first step kamu guna 2 angka bulat. The next step you use 3 significant figures, so on and so forth. So the final answer, if 10 people might have different final answer due to the significant figures. Tapi beza dia tak banyak. So you don't have to worry. I will still check and calculate using your own number. So if you calculate correctly, so you will not be punished lah kalau significant figures tu berlainan, jawapan akhir tu berlainan. Okay, sebab tu saya kata jangan tidur pada kawan kamu sebab macam previous semester, your seniors tend to copy and saya boleh tangkap dengan senang sebab tak mungkin kalau step dia 10 step, setiap step tu jawapan akhir tu sama. Sebab it's very rarely, memang impossible kalau setiap step tu dua orang tekan kalkulator, dua orang tekan kalkulator nombor yang sama. Especially macam, that's why I said, do not discuss and copy from your friend. I can catch it very easily. So sebelum dia berlaku kan saya kata saya nak tuduh, saya tak tuduh pun. Tapi just to reminder for you, kalau calculation ni, kalau tiru memang tak berbaloi lah sebab I can catch it very easily. So previous semester memang what I do, I will ask you to retest back. I bagi you soalan lain, set lain yang lebih susah. So do not copy from your friend, try to do it yourself, and at least I can really gauge. Katakan kalau macam the whole class are not doing well, so I will know how to adjust my teaching. I can adjust for the next test and so on. Tapi kalau all of you copy, bukan all lah, copy dapat markah tinggi, nanti the next question jadi lebih susah and so on and so forth. So please don't copy, because if I caught you copying, either you retest ataupun terus markah kosong, and I can catch copying very easily for reaction engineering. So saya beritahu dululah, okay? Right, so back to this. Right, so when you calculate this, okay, because it's a quadratic equation, you will actually get 2 answer. Kalau kamu ingat quadratic kan, kita kira kan kita akan dapat 2 nilai x, xe. Okay, so always you remember, you will have 2xe, of which 1 is definitely more than 1, 1 is less than 1. Memang biasa, kalau quadratic, kamu tahu mathematics, you have 2x, you have 1 more than 1, 1 less than 1. So kamu dah pernah belajar conversion, regardless conversion or equilibrium conversion, it can never be more than 1. 100% kan satu fraction dia. So you naturally will choose the x lesser than 1. So for example, in this case, the x, if you press your calculator, you will get either 0.096 or 1.9. So theoretically, you terus tahu 1.9 tu tak possible sebab tak mungkin conversion 190%. So the most possible one is below than 1. So you choose the xe1 as 0.096. So done on question number 1. So question number 2, the last one for today, we want to find the volume of CSTR. Okay, so let's check volume CSTR. Dia kata in this question, this reaction follows elementary rate law. So kalau follow elementary rate law, okay, dah senang lah. Kamu tahu, kamu kena ingat balik macam nak kira. Okay, so kamu tahu volume CSTR equals to FA0X per minus RA. Minus RA ni yang kamu kena faham. Kalau reversible, minus RA dia dah berlainan, dah tukar. Minus RA dia become, kalau elementary, reversible rate law. Minus RA equals to K in bracket, concentration of reactant, power stoichiometric coefficient, minus concentration of product, power stoichiometric coefficient, divided by Kc. So, kamu selesai dulu minus RA, kamu ganti dalam equation pun boleh. Sebenarnya adalah linear equation. Okay, so K kita dah tahu. Kita nak cari CA. Okay, nak cari CA ni kamu kena faham balik. Okay, kita nak cari CA kan. So, CA kalau kamu tengok, sama macam the previous equation yang equilibrium ni. Just that, kalau equilibrium punya concentration, we use equilibrium conversion. Kalau conversion untuk reactor, kita dah guna X. Hanya ada XE kalau cari CAE. Kalau nak cari CA, dia mesti X. So, mungkin you ask, what is the X? Kan dalam soalan kata, the conversion in the reactor is 85% of the equilibrium conversion. Maka, my reactor conversion X equals to 0.85, 85% of my equilibrium conversion. Equilibrium conversion saya 0.096. I multiply dengan 85%, 0.85. So, saya dapat reaktor saya punya conversion as 0.0816. So, kamu kena faham beza equilibrium conversion dengan reactor conversion. Equilibrium conversion hanya pada equilibrium. To find reactor punya volume ke, design ke, dia mesti pada X, your reactor conversion. So, you have to check information untuk tahu berapakah reactor conversion saya. So that I know my X, I can find my CA, I can find my CB. So, that's why tadi kita cari equilibrium conversion. Kita tahu equilibrium conversion, kita baru tahu reactor kita punya conversion. So, you find back your CA, CB using your reactor conversion. So, you replace, you get your minus RA, you replace in the volume CSTI yang kat bawah ni, kamu replace dengan nilai minus RA kamu. You eventually get the final volume of your reactor. So, I do admit that for the case of reversible reaction, dia punya rate law tu pening sikit, dan nak cari volume pun pening sikit, dan juga the first part nak cari equilibrium conversion pun a little bit of headache. So, tak apa, after this you got time, please look back again this one. And if you don't have, tak apa, nanti when the after semester break, we will discuss the tutorial. Okay, so before I finish the class for today, just a reminder again, this Thursday, please attend the lab demo at 10 o'clock. Please inform your friends. The attendance is compulsory sebab kalau you don't attend the lab punya demo, your attendance will not be recorded. So, kamu tak dapat lab ni, kamu tak boleh lah. It's a license for you to do your lab. Unless your friend has any reason, ask them to contact me personally. Okay, so pukul 10 hari Khamis. Rabu tutorial tak ada, saya cancelkan to give you time to do your mini project. Isnin depan pun tak ada kelas to give you time to study for your test. Your test is next Wednesday, 9:30 AM until 11. Questions will be emailed to your student email, UniKS student email, 15 minutes before the test. And once your test ends at 11, you are given 30 minutes to compile the answer. Please answer in a white piece of paper, scan, make sure the file in the combine, make sure in the form of PDF, submit kat VLE under test 1 submission. I will open for 30 minutes. By 11:30, the question has to be already submitted in the VLE. Okay, so details is on your Teams already, right? Okay, so that's all for today. So I will only see you, I will not even see you for the test, but I will communicate with you for the test next week. Okay, alright.